Okay, we're going to start since it's getting very late for online speakers in the US time zones. So really don't want to keep them up at night. So we are very pleased to welcome our next speaker, Rowan McAllister, who is currently a machine learning manager at the Toyota Research Institute in California, focusing on autonomous vehicle planning. Previously, he was a PhD student at the machine learning group with Carl Rasmussen and a postdoc in the robotic AI and learning lab with Sergey Levine, working on probabilistic modeling towards data efficient reinforcement learning and autonomous vehicle planning. We're very excited to have Rowan here from TRI, and let's give him a very warm welcome at BADUE workshop at IROS.
Well, thank you, Rohan, and all the other organizers, and for everyone for coming along today. So I wanted to talk about robust behavior models for autonomous driving. So I think one of the things about autonomous driving is there's different sources of uncertainty. And I think one of the real major ones is, what will other agents do in a multi-agent setting? So in many cases, we can perceive the world mostly fine. There's a little bit of uncertainty, but we can't perceive inside the heads of other people, other pedestrians, other vehicles. And so when it comes time to making predictions, we're often sure about the dynamics of our own vehicle, but we're really not sure what choices other pedestrians and vehicles are going to make. So in principle, we can, because of this inherent uncertainty, we can use probabilistic behavior models to at least build up some kind of data-driven model about, what decisions people might make in the future that we should be aware of for downstream planning. And this is great if these models are accurate, but for everything downstream, planning and so forth, it really hinges on whether these models are in fact accurate, where they need to be accurate in order to make safe decisions. So in order to consider the downstream effects of what models are doing, there's a couple works I'll talk about briefly today. In terms of robustifying these behavior prediction models or trajectory forecasting for the sake of usage downstream. So the fact that this might be used for planning. Okay, so I'll talk about one work here. And this is about control-aware prediction objectives. Okay, so consider the following scene, where imagine you're an autonomous vehicle and you're driving down this road just here. We probably want to be able to predict what other agents may do in the scene to anticipate their behavior in order to come up with a safe decision. So there's plenty of pedestrians here, but I want you to imagine this pedestrian over here. Consider our model predicts that the pedestrian walks this way, when in fact they actually walk this way. One question here is, does this prediction error matter? As opposed to a pedestrian, say over here, say we predict they'll walk up to a stop when in fact they run across the road to make the light. Does this prediction error matter? So this work is all about saying that second prediction error, even if it had the same L2 error as the first pedestrian, matters a whole lot more because they're suddenly in the path of where we intend to go. And a misprediction there could have real life consequences. Okay, so the problem here is generally that forecasting metrics are typically unaware of their downstream usage, which can be a problem. And the solution here that we came up with was actually very simple, which was to weigh the metrics by their effect on downstream control, to consider how they will be used. And so the benefit that we're really going for here is, can we improve forecasting or behavioral prediction where it matters? So in many instances, maybe the majority of instances, it doesn't really matter if you get something wrong, but in a select few, it's life or death. Okay, so some common metrics used in things like competitions or, publishing papers to kind of compare against other papers, things like average displacement error, often some kind of L2 difference between y hat, our prediction, and I'll use y as ground truth trajectories in our offline data sets, or the final displacement error at the last time step, or minimum versions of these, which are really useful for multimodal prediction metrics and loss functions, the miss rate, and then also for probabilistic models, the negative log likelihood. Now, there are some works that do consider how forecasting will be used downstream. And there's some different assumptions that different works will make. So some is, is the planner differentiable? This is really useful for end-to-end methods, obviously, or sensitivity analysis using the magnitude of gradients. Or is the planner stochastic? So this can be really useful for policy gradient methods. Or is the planner a known function? So in our work, we wanted to distinguish ourselves from some of the other literature and see if we could not make the first two assumptions, but make the last one. And the reason is that for a lot of companies, the planner can be very complicated and involve a lot of logic, a lot of if conditions. And so the planner is often not differentiable. And then for many reasons, for debuggability, interpretability, and so forth, you don't want it to be stochastic. You want it to make the same decision given the same inputs. And so we had a look at this one. And our solution was very simple. First of all, we compared against a baseline, which is the R2P2 trajectory forecasting method, a reparameterized push forward policy. It's a normalizing flow, autoregressive normalizing flow. And all we did was to take that existing objective and not change it. But in our methods, we came up with 3 methods here, was to simply take that likelihood and just weigh the batch by different ways. So the first method here, what we're doing is to look at what a policy, hopefully we can see my cursor, what a planner might do if it was fed ground truth predictions about where everyone may go, compared to what would the planner do if we do what we have to do online, which is to only feed predictions. Now, if this difference is large, that means there was something critical that happened. We should have, we were stopping when we shouldn't, or vice versa, or something like that. But if the prediction error doesn't matter, this would fall to 0, and so this would get weighed out of the batch. We also had a worst case version of this. So if we can take multiple samples, can we take over k samples? Can we look at the maximum distance between these two things? And then we also had an attention weighting method. So the attention weighting method was using Jean Macat's past work, who was involved in this paper. And it was really to look at these attention matrix between an ego vehicle and everything else when trying to do multi-agent prediction. And so by using these attention weights, we could kind of identify which were the important vehicles to predict correctly. So we've got an unprotected left turn, and then we're waiting for a car there before we go. And the setting here was just very simple. Carla, go down a highway. We scripted some pedestrians to cross the road. Sometimes they'd make some kind of random motions. And so the learning task was, can we learn when these pedestrians will cross? And if we can, then we have an intelligent driver model that will come up to a slow stop. So this is what it will look like once it's trained. The car's going down. You can see these attention weights. You can see that the pedestrians behind the vehicle, it's already learned that they're not important for the sake of safe decision making. It's really the pedestrians that are in front of it, and typically on the right-hand side who are closer to the curb. And it's not necessarily the pedestrians that are closest to the vehicle. So this is kind of what we want. And then the results look something like this. So we've got our baseline R2P2, and then we've got just R2P2 weighed by these different methods where we weigh the batch. And so what we found is that our first method of just weighing once with a single sample does a little bit better. This was over 100 trials, and so collisions in the base case was 11. We could bring it down to 7, but where we could really bring it down was this worst case scenario where we take multiple samples. If any of them would change the action, then that's important. So this is kind of necessary for probabilistic prediction where there's multiple things that may happen. The attention weighting didn't do quite as well, but I thought for illustrative purposes, we thought it would do better, but for illustrative purposes, it kind of gets the idea across. Like, can we visually see which pedestrians or vehicles matter most? And interestingly, this actually comes at the expense of traditional metrics. So for average displacement error, the baseline actually did the best. But our argument here is that that metric does not matter. It's really about the collisions that matter, that we care about. Okay, so I'll move on to the next paper, and so I guess for any questions we can, for both papers, we can maybe raise them at the end. So this next work was really a paper by Haruki Nishimura and Jean Macat, and this was about risk-aware prediction for robust planning. So imagine a similar scenario where we've still got a car going down the road, and there's some kind of, cyclist here. And given their past trajectory in gray, we're maybe 95% confident that they're going to continue down this road. But there is a small chance, maybe a 5% chance, that they're going to cross in front of us. So, we might want to be aware of that so we can start preemptively braking. So this is what, how we like to design autonomous vehicles. But what if that 5% was not 5%? What if it was 1%? Or what if it was 0.1%? Can our modeling still be aware of these low probability but safety critical events? So sometimes the really unlikely stuff is the really important stuff. And so if we're using sampling-based methods and it's a 0.1% chance, what does that mean? Does that mean we have to sample thousands and thousands of time online in real time to be able to, for our planner to consider these events? So that might be a bit of a problem. And so risk-aware planning is often about taking some policy and kind of policy evaluation and adapting it somehow, which I'll talk about in a second. So, okay, so we've got this cyclist here. They're probably going to turn right, but they may cross in front of our path. Now, what we can do is we can come up with a cost distribution here. So the main mode here is a low cost event, but then we've still got some probability mass on this high cost event. Now, what risk-aware planning will often do is make a pessimistic evaluation of this scenario. So often we would, take expected cost. This is very common. But what risk-aware planning is often, it often takes something that's between the expected cost and the worst case cost, some functional of that cost PDF to output a single number that can be our pessimistic cost. And this kind of helps us be a little bit aware of those tail events, which we might want to be aware of. And so what this work was to do was to actually say, can we flip the script a bit? Instead of taking many samples at planning time to compute this probability distribution, where maybe we need thousands in order to capture events that are 0.1% chance of occurring, can we instead change our model? So instead of a predictive model of where everyone may walk P, can we come up with a different model Q, such that the expected cost under Q is equal to this risk measure of the distribution of the random cost here. Now, why would we want to do this? One reason is that instead of taking thousands of samples online in real time, we can move the computational burden from the online deployment phase back into the offline training phase for our prediction model. So this can happen over many days with huge servers and take as much computation as we want to train up Q, such that at deployment, all we need to do is take a few samples, a handful of samples, and just take the expectation of that. And then we get something that would have been equivalent to had we taken thousands of samples online at deployment, which the compute on the car may not allow for. The second reason is that we don't have to change the planner if we want to introduce risk measures. We can bundle that into the predictive model. And this can be useful in large organizations where you're working on one thing, but not all things. Maybe you can't convince your planning team to kind of change these things, but you're in control of how the behavior prediction works. So you can isolate your changes to just that element in the stack. Okay, and so this is what it may look like. We have some kind of, even though the ground truth probability is 95%, our model can pessimistically think maybe that's only 60%, and this 5% could turn into 40%. And so the way in which we do this is we come up with a loss where this expectation under Q of the cost is equal to the this risk measure. So this is a constraint, and then we try to minimize the KL between our distribution here and the ground truth distribution, so that it still looks kind of appropriate. It's still got all of the modes. And the reason we do this is that this is an under specification, this constraint here. There's still many models Q that would satisfy this, including delta distributions that aren't so useful for interpretability. And so that's why we have the, on top of this satisfying this constraint, we would ideally want something that looks similar to the previous distribution. And our loss function is really just to soften this up. So instead of saying a strict equality here, we have some distance function between the two that we want to minimize, together with a hyperparameter over the KL between these two distributions. And so some example risk measures, which I'll just maybe skip over quite fast, is so risk measures are usually some kind of value, output some value between the expected cost and the maximum cost. So something that's kind of a bit pessimistic. Entropic risk is popular, so that's kind of like a soft maximum. There's also conditional value at risk, which looks a little bit complicated, but it's really related to expected improvement in the Bayesian optimization literature for those familiar. So it's really just saying, give me a for the user, tell me some hyperparameter value, like 0.95, the 95th percentile. And out of this cost distribution, from this point onwards, I'm just going to compute what was the expected cost. So rather than the whole distribution, it's just from the 95th percentile. And so the CVAR would be something like here, as opposed to something like the mean cost over here. And so for a didactic case, we've got a pedestrian crossing the road. Hopefully they cross fast into the green zone, not slow into the red zone where we might collide. And we've got two distributions here on how far they walk. There's red, which is bad, green, which is good. Our kind of VAE model will kind of model both modes. It's not perfect, but it's okay. But then the risk bias prediction is really kind of promoting that red mode, which is what we want. And just in the interest of time, I'll skip over a little bit. The risk estimation error that we find looks something like this, where for a regular inference, we might need more samples in order to drive the risk estimation to 0. But with our model, we only have to use a few samples to get a more accurate estimate. And the greater this is, the more the tails that you're looking at, so like the 95th percentile or the 99th percentile or 99.9th percentile, the more samples you'll need if you're just doing vanilla inference. I think I'm almost out of time, so I'll just finish up on some of these slides. This is what it looks like on real data. So this is the Waymo open motion data set. And so we can see, so we've got our ego vehicle in blue and our ADO vehicle in green. And this is what regular predictions look like. We're in a lane that is supposed to be turning right here. So a lot of the predictions going down here quite fast. And if we bump up this risk level, which is a user input hyperparameter, the sigma we were talking about before, so maybe 50th percentile here, we can see that the car's not going as fast now. And so what that means is we may clip it. It may not get out of the way in time. And then if we really go higher, so risk level 95%, suddenly we're predicting this car is just going to collide with us. So if we really care about these kinds of events, we can take you can see we only have to take one sample from this to be able to consider that event. That was actually quite rare. Yeah, different kind of situations here. Again, will the green car get out of the way of our blue car going around? Risk neutral, it looks like it'll get out of the way. When we start bumping up the risk, it looks like it's not going to get out of the way in time, and so forth. And then I'll leave this as my last slide. So yeah, I think this is similar to the one we saw before, but just a few different more risk levels. So the more we bump up the risk, the more we can see that maybe this green car will do something illegal that it's not supposed to do in this lane, and actually maybe decide that they should go left or straight forward or something like that, especially at the really high risk levels. So yeah, thank you to my team, Blake, Logan, John, Haruki, Sergey, and Adrian. And yeah, any questions, please let me know.
Thank you so much, Rowan. That was a fantastic talk. And we can now open the floor for questions. Anyone who wants to ask a question can come up to the mic. We also invite questions on Zoom. So maybe, Rowan, I can start it off. So in the first part of your talk, you mentioned about, control-aware trajectory prediction and how we want to incorporate the trajectory prediction into the planning part. So one question, implementation-wise and just intuition level-wise, is does it make more sense to incorporate the learned representations that come from prediction directly into planning, or the outputs of trajectory prediction into planning, which makes more sense in terms of higher success rate or more accurate planning, I would say?
Yeah, that's a good question. I'm not going to give you a great answer here because I don't really know. I think it's not obvious to me what the method is. I think we were just assuming that there was some kind of input to a planner. And in our case, we just said, what if we gave it the trajectory, a sequence of locations, perhaps some more kind of latent information that contains more information about the state of the driver, where have they been looking, and so forth, might give greater context. And we simplified the problem in assuming that prediction happens before planning and that there's no interaction-aware planning. So we assumed humans move as they would, and our job was just to get out of the way. Yeah.
Gotcha. That makes a lot of sense. We have a question in the chat. Okay, I can probably read it out. So Max is asking, is it necessary to have samples of equal probability? Couldn't you use samples with 5% probability each for the regular and 0.05% each for the unlikely?
Yeah, I think, this is a good question. And I think this is actually, you can do this with discrete systems. So if to your previous point about like latent variables, if you've often discrete, like categorical distributions have been popular to really capture different modes. And when you've got some kind of discrete representation, you can just enumerate through the finite many values that they can take on and look at these different probabilities for different types of behavior. And in that case, you certainly could. So our case really only applies for the more continuous setting. So if there's an infinite number of modes, or and you're just trying to come up with some continuous latent representation or continuous trajectory space modeling.
Okay, so Larry also wants to ask a question. Is the cost function you mentioned handcrafted?
In these cases, yes, they were. Yes. So yeah, we'd look at things like time to collision and so forth. But yeah, it certainly not obvious what cost functions should be in autonomous driving. That's a whole area itself. Yeah.
Okay. Yes, we have a question.
Yeah, I'm wondering, in the second work, we had the examples of predictions that come from like higher risk levels. I forget exactly how the algorithm works, so I'm wondering, do you need to train a different model at each risk level, or can you take a trained model and that's an input and you can generate kind of like one worst case prediction and then 9, more likely predictions?
Yeah, so I think, it's a great question. I was wondering about that. I initially pushed for like, let's just have a different model for different risk levels, but eventually we just ended up putting it as an input and would put it as like a logarithmic input so that, 0.99 was very, very different to 0.999. And the model understood that, but and then we just completely left that up to the user as to like what kind of risk do they want to accept. And one of the ideas that we never actually moved on was like, if different people drive different ways, can we actually just back calculate what their sigma value was? Like how much risk do they like to accept from their data, their personalized data? And then we could set the hyperparameter that way as opposed to, trying to figure it out ourselves.
Thank you.
Thanks.
I think Max has a follow-up. So Max asks, maybe sets could help to this end, discretizing the continuous trajectory space.
Yep.
Okay.
Yeah, and I think when you've got sets or anything discrete, then this isn't a problem anymore. You can just enumerate through all of them, even the very low probability ones. Yeah, that's right.
Okay. So we have one more question. Yes, maybe this could be the last one, but yeah, go ahead.
Yeah, a really quick one. I'm assuming there's no magic here, but kind of piggybacking off of that previous question over here at this mic, in order to be able to kind of predict, when you train those models, in order to be able to kind of predict some of those, very unlikely situations, you would need to have that is somewhere in your data in some manner. So I suppose there's probably no magic here, but there's nothing that gets you around not having examples of let's say the wackiest behavior or
that's
something.
Right. Yeah, that's correct. And I assume for these kind of models, maybe it captures the 1 in 10,000 events. Like as long as you've got enough of them that your model could be trained, a long time offline with taking thousands of samples. But I think there will be a limit where, the very, very tail stuff, it just won't capture. Maybe no matter how much compute you have, and especially to your point, the stuff that it hasn't seen, then there's no hope. Yeah.
Got it. Okay, thanks.
Yeah.
All right, let's thank the speaker once again. Thank you so much, Rowan, for a wonderful talk.
Thank you.
Okay, so now our next speaker is again online. He's Nicholas Rhinehart, who is a postdoctoral scholar at UC Berkeley. He works with Sergey Levine. He's broadly interested in the fields of machine learning, computer vision, robotics, and specifically interested in the topics of imitation learning, deep conditional generative models, RL, and planning. Next research aims to build highly capable autonomous systems that learn to both accurately forecast outcomes and reliably use this understanding to make good decisions in new situations. He got his PhD in robotics from CMU, and he was awarded a fellowship from CMU. And he's got a number of best papers and best paper award mentions. There are too many to list over here, but we're just going to welcome Nick on stage. And Nick, yes, the floor is yours.
Okay, yeah, thank you for the introduction and thanks for having me. Yeah, happy, really excited to talk about some new work today in this presentation. Yeah, I'll just jump right into it. There's basically 2 papers that I'm talking about today. One is contingencies from observations. I'll refer to it as that. And then there's this other one called Is Anyone There? That also involves contingency planning. So what this talk revolves around is this idea of contingency planning. So what's contingency planning? So what we're doing in with contingency planning is basically I'll set it up with this scenario that it's useful for. So in this scenario, imagine we have some autonomous system that's going to guide this car that's close to the camera viewing the scene. And then we have some oncoming car, let's say driven by a human. And we want our autonomous system to navigate this robot vehicle through an unprotected left turn. So this oncoming car may or may not yield to our robot. So the decision tree that I'm going to show to you next represents possible sequences of robot and human decisions for this unprotected left turn. First, if the robot decides to wait outside the intersection, then the other car, the human-driven car, we're saying, deterministically passes through the intersection, and then the robot turns, and then we'll say it arrives late for a return of 0. Or if the robot decides to enter the intersection slowly, the human-controlled car may or may not yield to the robot, and the robot either passes through the intersection first to arrive on time and receive a return of 1, or it passes through the intersection second to arrive late and then receive a return of 0. And then finally, if the robot decides to enter the intersection aggressively, the human-controlled car may or may not yield to the robot, and then the robot either arrives early, receiving a return of 2, or the human-controlled car can't brake in time, and the result is a near collision. Then the robot receives a return of -100 in this example. Okay, so let's think about how the robot could plan and achieve high return in this situation. So if the robot had to plan a fixed sequence of actions ahead of time, I'll call this an open loop non-contingent plan, in that it is open loop, not reacting to what may happen in the scene. The best open loop plan here would be to wait outside the intersection and never arrive early, because of the unresolved human stochasticity. The human may or may not yield to the robot if it enters the intersection. So for this plan, the robot could accurately predict the value to be 0. So it predicts the value to be 0 and its actual value is 0 when it executes this plan. If instead the robot was overly confident in its ability to make the human yield, let's say it has learned a joint model of behavior and it's planning every agent's behavior in that model, this planner would produce a plan that always turns before the human and predict that this plan would yield it a value of 2. But this value prediction would be an overestimate, because in reality, in this example, the human doesn't yield 50% of the time, which leads to a true negative value, or a true value of -49, because of that high cost of near collisions. And then finally, instead, with a closed loop contingent plan, the robot can potentially arrive earlier than the basically the open loop planner by planning to enter the intersection first with a contingency plan for different behaviors it may observe the human to do. So it would accurately predict this contingent plan's value to be 0.5, which is higher than the real value of any other plan. So if the human chooses to yield, the robot would proceed to make the turn in front of the human. Otherwise, the robot waits for the human to pass. So this contingent plan causes the robot to enter the intersection and wait to see what the human does. So in order to enable this type of planning based on what the other agents may do, we need a model of multi-agent behavior. And here's what we want this model to do. We have as input a single latent robot plan, as well as some scene conditioning, let's say from an RGB camera. The model also incorporates as input uncertainty about what the other agents may do. For one realization of that uncertainty, the single robot plan results in a specific joint trajectory. And then for a different realization of what the other agents may do, the single robot plan results in a different joint trajectory. So if we can design a model in this way, the challenge of contingency planning is reduced to the challenge of identifying a single robot plan in the planning space that results in high quality trajectory space plans in expectation. So where does our model come from? We designed our model based on an existing model of multi-agent trajectories that can be used to compute exact probability densities of joint trajectories. So I'll refer to this as the precog model from our paper, ICSV 2019 paper, and it uses a normalizing flow as a learnable transformation from a base space of Gaussian random variables, so the z's in this diagram, to the joint trajectory spaces, which are the joint trajectory is the concatenation of all the s's in this diagram. So we needed this property of the ability to compute exact likelihoods in order to use the model's probability as part of a planning criterion. So a 2-agent version of the model is shown here, although the model can generally be used for a variable number of other agents. The way this model works is that it allocates uncertainty for each agent's decision at every step in time and conditions each of these uncertainties based on the temporally available information. So essentially it factorizes uncertainty over agents and over time. The z variables at each time step, I'll call them latent variables, although they're technically not latent variables. They correspond to an agent's control of the next action that it can take. So in the model, each agent's position depends on this z, the latent control, and the most recently predicted positions of itself and of all other agents. So in this 2-agent model, if we decide latent values for one of the agents, like our robot car, then we've decided how the robot will react to what it sees in the future. So that's exactly what a contingent plan is, a plan for how the robot will react to different possible futures. So in order to perform this conditional planning, it's essentially a matter of choosing good Z's under some planning criterion. So one way of basically deriving our planning criterion is to set it up as a posterior inference problem in which we have some posterior over planning variables. So the Z's that form up the plan that's conditioned on information about the scene, the O, as well as some information about goals or the planning objective, which is the G here. So if we apply Bayes' rule, drop constants and lower bound this, we get a final optimization problem in terms of the two distributions. You have your prior and your likelihood. The prior is where the model enters in. So this is a model of joint trajectories. And then we have our likelihood, which is where you can incorporate standard motion planning objective terms like we want our robot to reach some specific destination, and you can also incorporate constraints on the trajectories, like planning to ensure some minimum distance between the robot and all other vehicles. Okay, so we have these two terms. The first one is learned, and the second one is designed. And the learning of that prior is essentially capturing what it estimates as likely joint trajectories in the based on the training data. Okay, so the way that we evaluated this planner is using Carla. So we have some perceptual input, and we came up with a set of scenarios that require contingency planning in order to perform well. So I'm going to kind of step through the outcomes in a few of these scenarios now. So in our experiments, basically we designed these outcomes, we designed the scenarios, and then we collected data from each of the outcomes in order to train the model. So I'll show you some of the outcomes now. First, there's this overtaking scenario. The robot's trying to overtake the human by first switching into the left lane and then switching into the right lane after it's passed the human. So in this scenario, the human may slow down to facilitate the overtake, or the human could choose to speed up to prevent the robot from overtaking it, as shown on this video on the left. The robot should then yield to the person and stop trying to overtake them. That's what we say is good behavior or a good outcome in this case. Or the robot could try to aggressively pass the human without seeing if they'll yield. And so what makes this aggressive is that in some situations, the human can't brake in time. So the robot aggressively overtakes, no matter if the human is yielding or not. And then in this scenario, the human is basically unable to brake in time, and it results in a near collision. And then finally, the robot could choose to be passive and not attempt to pass the human at all. So all of these scenarios have this structure of essentially the best contingent plan has different behavior based on whether or not the human essentially yields to the robot. The passive plan always gets to the destination, but is sometimes slow. And then the aggressive plan sometimes gets to the destination quickly, but sometimes results in a near collision. This same sort of structure appears for an unprotected right turn. So at the bottom, the robot is entering the intersection to see if the human will yield to it or not. And in the bottom right, I think the human, it does yield to the robot. And so then the robot turns, and then the bottom left, the opposite happens. Okay, and then finally, we have the original left turn scenario that I used as kind of our motivating example, in which the robot has to enter the intersection in order to observe whether or not the human will yield to it. So now I'll kind of step through how our method works. There's two main phases. There's the training phase and then the deployment. The model at the training phase is learned from multi-agent demonstrations. So trajectory demonstrations. And these are paired with high dimensional observations of the environment. So for this model, we use the same learning technique as the original precog model, except now the visual input is an RGB image rather than a LiDAR image. It's, I guess, a small difference from our perspective of really focusing on how we use this for planning. Okay, and then at deployment, we have that cost function that I showed you earlier that is a function of the model's probability density function. And that shows up in the contingency planner in that LCFO objective is where that that represents the planning criterion. So that planning criterion takes as input information from some outer planner that tells the robot where to go at a high level, as well as the information from the environment, so the image of the environment. And then the contingency planner is used in a receding horizon fashion in which it outputs a policy, which is our contingent plan, which then is used to produce the next target position of the robot, which is then tracked with a P controller. Okay, so you have a standard receding horizon control setup for the output of the contingency planner. So in our scenarios, we compared this contingency planning approach against several other approaches in closed loop control settings. So we measured a couple of things here. We measured whether each approach can reach a goal, denoted RG, and reach it optimally, so quickly and safely, which we denote RG star. So in order to perform well, the robot has to recognize what sort of situation it's in based on its visual and its position input in order to generalize beyond the training situations. So we observed the expected failure modes of each of the non-contingent planners. So one of them is the single agent baseline, which is from our iClear 2020 paper that used a normalizing flow-based model as a planning cost function. And this single agent baseline doesn't model the other agents and is therefore expected to reproduce with some frequency risky behaviors seen in the training data because it doesn't explicitly model the uncertain behaviors of the others and therefore cannot incorporate terms in its cost function that basically involve constraints between the robot and these other agents. And then we have our original, and there are also ways to use the multi-agent model in a non-contingent way. For instance, the overconfident or the L joint objective is results in often colliding because it assumes the planning objective essentially assumes that the robot can control the behavior of the other agents, but obviously that assumption doesn't hold up in practice. Okay, so we have this method for contingency planning based on the uncertain behavior of currently perceived agents. But what happens if we try to use it when our robot can't sense relevant agents? So in this scenario that I'm showing here, at a so-called blind intersection, the robot can't perceive an oncoming car without first nudging forward ahead to see the car. So this is another type of contingency planning that we want, or that autonomous cars need to be able to perform, essentially contingency planning that involves information gathering to handle perceptual uncertainty. So a good human driver in this scenario would slowly inch forward to improve their visibility of the oncoming traffic before deciding whether to proceed. So basically, the question in this next work is, can we develop an approach in which this type of information gathering occurs naturally when needed as part of a machine learning driven planning framework? Okay, so this work will appear at Coral 2022 later this year. So one way to view our task is that of learning a plannable model of two different types of uncertainty. Uncertainty in the existence of the other agents, as well as uncertainty in the intention of the other agent's behavior. So we had that latter uncertainty before. We modeled the uncertainty of the intention of other perceived agents' behaviors. And we can view these two types of uncertainties as a mixture of, one of them is discrete and one of them is continuous. And then there are two ways to think about what we want planning with this model to do. The first is we can view it as we want to plan contingencies for hypothetical agents. And another more general way of thinking about this is that contingency planning should naturally invoke information gathering to resolve relevant perceptual uncertainty. Okay, so those are kind of two different interpretations of what a good contingency plan should be doing. So let's look at how we can adapt our previous method of contingency planning to solve this problem. So in our previous work, the goal was to learn a model of multi-agent behavior that can be used for contingency planning. And then the input to the model to learn it is the set of expert observations. And then planning it is performed by optimizing these Z variables in the model for the robot under the uncertainty of the other agent's behaviors. So in order to learn a model from observations, we extended this model to model the detection of other agents as a function of past positions of all of the agents. So by modeling detection instead of existence, it allows us to simply mask out the positions of undetected agents during training and model inference. So basically, we have everything we need during training time to learn a model both of detection and predicted position. So we're forecasting detection and position. So like before, the model is conditioned on an observed ego agent trajectory, as well as perceptual information about the scene. And then in this model, we're using a LiDAR range map as the perceptual input. So this setup enables the model to associate patterns in perception, like potential occlusions, with potentially dangerous unseen agents. So when using it for planning, it provides the planner agency over perceptual uncertainty. The robot can plan to influence future detections. This diagram shows a bit more information about how the model is implemented. The model architecture is similar to the previous model, and then the major difference is that inclusion of the predictions of agent existence. So on the right, we see 3 joint trajectory samples from the model. The top sample shows a joint trajectory rollout of a potential future in which no other agent appears. The bottom samples show different possible futures in which another agent is detected and either is or is not yielded to by the robot. So in order to evaluate our method, we designed a few benchmark scenarios in the Carla simulator again. Each scenario involves a potential occlusion that requires the robot to be reactive in order for it to perform well. So this potential occlusion is constructed so that it causes the version of the planner that doesn't reason about occlusion to fail. So a benchmark of these types of scenarios with visual input didn't already exist, so we had to create our own. So I'll show a few outcomes from one of the scenarios, this 2-car intersection scenario. On the left are 2 possible expert outcomes in which the expert slightly reduces speed as it approaches the intersection in order to give itself an appropriate amount of stopping time. And then the video on the top right illustrates an overconfident outcome in the training data, in which the robot acts as if there will not be another vehicle that can enter the intersection in front of it. And then in this outcome, there is another vehicle around the corner, and it results in a collision. Okay, so we constructed 4 of these types of scenarios in Carla and compared our approach against 4 baselines. Each approach or each scenario consists of 30 randomized trials. In each trial, we measure whether the vehicle reaches the goal, denoted RG, and reaches it optimally, denoted RG star. So when the vehicle does not reach the goal, it's because it collided. And we also measured, the collision frequency of each approach, as well as the average time to goal of each approach's successful runs. So we have a baseline called the overly conservative reference driver, which we implemented by hand deterministically, and it always reaches the goal, but never reaches it optimally. So this serves as a reference for the average time to goal. The single agent model baseline, which again is from the iClear 2020 paper, deep imitative models. It uses a normalizing flow as a planning cost function, and it doesn't model the other agents. So we don't have any of the uncertainties about other agents, neither behavioral uncertainties nor perceptual uncertainties. So it ends up reproducing with some frequency risky behavior seen in the training data. And then we have our multi-agent model from the contingencies from observations paper, which doesn't model the potential appearance of currently unobserved agents. It also performs some risky behaviors because it, again, doesn't model all of the uncertainties that it needs to. The uncertainty in perception is what it needs here. So therefore, it cannot plan to be contingent upon the potential appearance of currently unobserved agents. And then we also have a 2-agent so-called game theoretic active perception planner that's been applied to some of these similar scenarios in the past. This planner assumes perceptual pre-processing and hand-defined models of behavior, so it's not learned and it doesn't process raw observations. So it's kind of a little bit hand-intensive to set up for each scenario. So it treats the planning problem as a 2-agent zero-sum game. So in order to apply it to the scenario with more than 2 agents, so we have a 3-agent intersection scenario, the planner solves multiple 2-agent games by assuming each solution is independent, which can lead to overconfident behavior. And then finally, we found our main method was able to achieve near expert level behavior overall in these scenarios, which basically just means that it was able to realize an accurate model of behavioral and perceptual uncertainty that it could use for planning. And one promising direction of future work would be the automatic construction of a much larger benchmark of these types of difficult planning scenarios, with more variation in the number of agents in the scene, as well as more variation in the types of scenarios that require this type of contingency plan. Okay, so that's all I wanted to talk about today. You can visit this site here to read the paper and get the code once we release them later. Yeah, and now hopefully we have a little bit of time for questions. Thanks.
All right, let's thank the speaker. Thank you so much, Nick, for taking our time. So we have a question from the chat. Can you elaborate on how your method relates to POM-DP solving with MCTS? Yeah, you can think of it as an approximate method for doing just that. And it's essentially learning a part of the system dynamics by learning this model of multi-agent behavior, but it's the system dynamics is perceptually conditioned. So it processes this, in our case, the LiDAR range map. And you can think of MCTS as one way to do contingency planning. In general, that's going to consider the basically the entire space of contingent policies. Whereas in our approach for contingency planning, we are planning basically a very small subset of the parameters of policies, and the model is essentially restricting the things that we consider for planning as the behaviors that it's seen in the training data rather than the space of all possible actions. So they're pretty related. And you could come up with a way to solve it if you had some way to basically represent the scene and plug that into some learned system dynamics, or some system dynamics that you got from somewhere. Does that make sense? How they connect? Thanks. Thanks. So yeah, so maybe we can follow up. Max, you can follow up with Nick maybe offline. We have one in-person question. Maybe we can have that as the last quick question. So yeah, go ahead.
Hey, Nick, quick question. So I guess I wanted to understand how the learned contingency plan is affected by really imbalanced rates of occurrence of different agent types, like say very few agents are aggressive and most agents are passive. Is that something that ends up being considered in sort of maybe how does the relative reward of passing in the agent quickly versus sort of passing the agent more slowly affect that?
Yeah, so the way the planning is done is the planning criterion is just under the expectation of the uncertainty of the other agents. So you could come up with planners that are more conservative than that. And for instance, if the model, if you're planning in expectation rather than with respect to some risk threshold, like what Rowan was talking about before, then you could definitely end up with cases where in expectation it's good, but planning in expectation probably isn't what you want to do in the end.
I see. Thanks.
All right, thank you, Nick. Thanks for giving your time and speaking at our workshop. So now we're going to be playing the talks for the spotlight talks. And let me quickly share my screen. And I'm going to be playing the first talk. Where to go? Okay, so the first spotlight talk is by Laura Zhang and the authors of University of Maryland at College Park. And the talk will focus on exploring contrastive learning and attention networks for self-driving and generalization. This is a video that we'll be playing, and Laura will be available for Q&A afterwards. The audio playing?
I cannot hear the audio, Rohan.
Yeah, let's see. Play the audio, right? Why is it not playing the audio?
No.
I think it's working now. Yeah.
I think we still can't hear on Zoom.
Laura, do you think you can give the talk like live? Like you have do you have a script ready or?
Yeah, I could just pull it up. I could just go off the video really quick.
Okay, so you'll share your screen, right?
Yeah, I could share my screen.
Okay.
I'll pull it up right now. Oh, actually, I think I heard the audio briefly from your end, or maybe actually no, sorry, that was from my end.
And maybe you can also play the video in your side and share the computer audio with us.
Okay, let me try that. 1 second.
Or I can play the video, like whichever is easier for you. I can play the video and you can talk over it, or you can share the slides or the video yourself.
I can definitely play the video from my end. Just have to pull it up really quick. Okay, so I'm going to share my screen now.
Yep.
Can you guys see my screen?
Yes.
Okay.
Oh, Laura, you're muted. Could you unmute yourself?
Oh, yeah.
Yep.
Oh, can you hear the audio from the video?
Could you play it?
Yes.
We cannot. I think there's a problem.
Oh,
with the
okay.
video.
That's fine. I'll just share my PowerPoint. I think that's easier.
Okay.
Hello? Okay. Oops. The video, sorry. My audio is playing in the PowerPoint as well. I'll just share from this side. Okay, so I'm going to talk about exploring contrastive learning and attention networks for self-driving. So this is mostly for vision-based end-to-end driving. And the motivation is that a lot of, especially for imitation learning, there's edge cases which are very hard to encounter in the real world. Things like aggressive driving and close call encounters. And then also undefined driver and pedestrian behavior. I think a lot of the previous works from other talks at the workshop have also covered this. So for things which are data-driven, it's very difficult to get these kinds of cases in the real world, and if at all, probably impossible. And these can be addressed in simulation, but the question is whether whatever we address in simulation will be effective in the real world. And so transformer architectures seem to offer some promising results in terms of generalization compared to CNN-based models. And then also contrastive learning objective enforces similar samples to have similar representations in feature space. So this is kind of an exploratory work on seeing how these concepts work in context of vision-based driving. And so the way that we formulate contrastive learning in this sense is we want to add some kind of temporal aspect to it. And in traditional contrastive learning, there is some level of, there's some kind of hard label of similarity. So in image classification, the same class will be considered positive, where different classes will be negative compared to an anchor sample. And so in the case of driving, we can consider the temporal samples as like the vector of, for example, steering angles to be representative of a sample. And we can use some soft labels such as cosine similarity to have some kind of soft label for contrastive learning instead of the hard label. And so the intuition here is that, for example, in simulation versus real world, we ultimately turning left in the virtual world is also the same as turning left in the real world. And given that the labels are normalized, the label space should be pretty much the same. So we want to enforce that, you know, the features that the model is learning is generalized to both virtual and real world. So from the results, we see that different architectures handle spatial-temporal features differently. And so here, plus contrastive is with control-based contrastive learning. And plus vanilla is vanilla transfer learning, where source model is trained on Carla and the target model is trained on Waymo. And we can see here that contrastive learning seems to benefit VI-VIT architecture the most, and that the key difference between VI-VIT and Timesformer is that VI-VIT has separate spatial and temporal encoders, whereas Timesformer encodes spatial and temporal dimensions together. Okay. So now we ask ourselves, how do the generalization of attention-based architectures compare when trained from scratch? So the table below shows zero-shot generalization from several test data sets. And yeah, this is pretty much it. And as we can see here, the results are pretty underwhelming in terms of the transformer architectures. And that's not anything particularly surprising from my end, since I find that a lot of the data sets are not as large as the ones from the original VIT papers, which show the massive, or at least the benefits of generalization for these transformer architectures. And as the original VIT authors quote, vision transformers do not generalize well when trained on insufficient amounts of data. And in this case, compared to the tasks that VIT transformers learned in the original paper, at least the domain of real world driving is much more constrained and specific. For example, you'll always have like those road features, those road lines, skyline, things like that. So the diversity is definitely much more constrained in this case. And so for limitations, including thoughts, current real world driving data sets may not be large enough for attention-based networks, at least for sim to real. So the first challenge is that in order to address sim to real is making sure that we have large enough real world data sets. And then one limitation of these results is that we currently only use single view images in unimodal learning. So it could be the complexity of the task is also limiting of the results that we got. And also transformers have seen success in methods purely in simulation, such as transfuser, but training from scratch is also incredibly difficult and expensive compared to CNN-based models. And also contrastive learning is an interesting angle for adjusting sim to real generalization for vision-based control. I haven't really seen much in relevant literature, but I think using the soft labels in terms of the control sequences as vectors could be an interesting angle to explore in the future. Okay, I think that's it. So,
all right, let's thank the speaker.
Any questions?
So now we can open for questions. If you have questions, please come to the mic. Laura, maybe I can start with a quick question. So transformers typically need a lot of data for during the training, right? And moreover, like in a lot of the steering data, the steering values are typically very similar. So when you train, did you face any issues during training due to these two issues? One, transformers needing a lot of data, and two, the steering values are pretty similar, so there's not much diversity in the data to distinguish or discriminate during training.
Yeah, definitely. I think that was like, I guess the main takeaway, which almost seems like expected. Well, not expected, but we did try to train models on data sets like Waymo. It's like Waymo's data set is not to be very large. And even for trained on Waymo data set, like here for the zero-shot generalization, the traditional CNN model with, so the original NVIDIA CNN plus LSTM architecture, it was still able to generalize better in the same training circumstances compared to transformer networks, which in the differences were pretty surprising to me. But I think it is due to limitation of the diversity and at least the size of the data sets. And I think that it's definitely more constrained, like the task itself is more constrained than, for example, the general vision tasks of classification and things like that. So for example, here, no matter if we're in virtual or real world samples, the view and the features of each image will be much more like less diverse compared to images such as for image classification, where there could be different views and angles of an image. Also more constrained is the methods of augmentation that you can use for steering, because oftentimes the angle of viewing that you're looking at for steering can greatly affect also the actual prediction that you want itself. So it's not like exactly like traditional image tasks where you can crop and transform. Those things may actually matter for things like driving. So it's definitely much harder to use, to at least use engineering tricks to address it with transformers.
All right. Thank you so much, Laura. And yeah, thank you for a great talk. So
Thanks.
now we're going to start with the next spotlight, and let's see how this works. So the next spotlight is going to be, let me first share my screen, and where is it? Share sound. Okay, so let's see if this works. The next talk is going to be on inverse reinforcement learning with hybrid weight trust region optimization and curriculum learning for autonomous maneuvering. This is the honorable mention for Best Paper Award, and this is by Yushen Wei-Zi Li and Ming Lin from the University of Maryland and University of Memphis. So I'm going to play this. Out there on this, and you can mute out there on this.
Yes.
Seems I cannot hear the voice clearly.
Okay, so comment on. Hello. Yeah. Could you comment on the sample efficiency of your approach? And more specifically, how many expert demonstrations do you require?
For the expert demonstration, in our experiment, we collect about 10,000 level steps for the experts in one scenario, like because we have several scenarios. So for each scenario training, we collect about 10 to 20 steps of the expert data. And for the sample efficiency, if you mean the expert sample is like relatively real time, and for the online training, since we have two simulators, one is the lightweight simulator. This is specifically designed for the R training. So there's no there's no camera, no RGB images or rendering process. So the efficiency will be relatively quick, efficient.
Okay, thanks, Ishan. So for our next, I think for the following spotlight talks, we're going to have the spotlight speakers themselves share their recorded videos with sound, and they can be present live for Q&A. So the next spotlight talk is the Best Paper Award winner, Imitative Planning Using Conditional Normalizing Flow by Shubhankar Agarwal et al. And okay, so let's see. Shubhankar, can you let me unmute you?
Should I play?
Yeah, go ahead.
Hi, I am Shubhankar Agarwal. Can you guys hear it?
Yep.
Cool. And I'll be presenting our work imitative planning using conditional normalizing flow. Let's start with motivation. One of the most popular methods for motion planning in unstructured environments is sampling-based planning, where we uniformly sample trajectories and run them through a white box costing functions to pick the min cost trajectory. These kind of methods are interpretable because of the white box cost functions. However, these methods are not sample efficient and do not use the same concept. Another popular approach is imitation learning, where we learn a mapping between sensor data such as LiDAR or camera and human demonstrated trajectory. Since these methods use scene context, they are very sample efficient. However, these methods provide no human interpretation into why a trajectory is selected. Also, they do not generalize to real-world scenarios since they can only learn from a single human demonstration for a given complex self-driving scenario. Let's discuss some preliminaries. In this work, we modeled the planning problem as a POM-DP, where the planning cost surface J is modeled as a Boltzmann distribution. We also use normalizing flow in this work, which consists of a series of invertible transformations which map a known prior distribution Z0 on the left to a potentially complex target distribution ZK on the right. In this work, the complex target distribution ZK is the planning cost surface. Let's look at our method, which we call flow plan for a general self-driving system. Starting from the left, for a given sensor data, the perception system in blue generates object detections and future actions of other actors. Using these outputs, a white box planner in green samples trajectories and picks the min cost trajectory. We introduce our method flow plan in red, where for a given scene and samples from known distribution Z0, we learn to sample low cost trajectories. Specifically, we use normalizing flows to sample trajectories which have a low cost in the planning cost surface. During training, we backpropagate to minimize the KL divergence between the planner cost surface and normalizing flow learned distribution. Our method flow plan is significantly more sample efficient compared to white box planner since it is scene dependent. The sample trajectories are learned through a white box planner and thus are interpretable as well. Finally, our method is easy to train compared to imitation learning. During training, we can sample and learn from a lot of trajectories for a given self-driving scenario instead of learning from a single human demonstration as done in imitation learning. Let's look into our method's performance against other approaches on a challenging real-world dataset. In this plot, we have number of samples in x-axis and planning cost in y-axis. We show our method flow plan in yellow is significantly more sample efficient compared to sample-based planner in blue and imitation learning in red. Our method achieves lowest planner cost with fewer samples compared to other methods. Thank you.
Thanks, Shubhankar. So now, does anyone have any questions for Shubhankar? Yep, go ahead.
Yeah, I think I missed it just because it was going by pretty quickly. But why is it that you know exactly why the sampler chose the sample that it chose? You said that it was interpretable and you made a point about like, you know exactly why.
Oh, okay, yeah. So what I mean is like usually like let's say if I sample from a distribution, like in imitation learning, you just pick a trajectory. But here we can, let's say if I sample 50 trajectories, you can know, okay, this one had a collision, that's why it was not picked, or my gains for this cost is really high, so I can go and tune those gains. So in this way, like if you have these white box costing functions, you know exactly why a trajectory wasn't picked or was picked.
Oh, I see. Okay, so you're talking about why, like the evaluation at the end rather than the actual sampling of that trajectory from the conditional variable encoder.
Right, and additionally, like since you can get the log likelihoods from normalizing flow, you can use that too. I didn't show that plot, but in our paper, we have a plot about how if we keep sampling around trajectories which have higher log likelihood, we can get lower cost trajectories from that as well. So we can have both scores from that and white box.
Okay, cool. Thanks.
Okay, thanks, Shubhankar, for your talk. So the next talk, spotlight talk, is going to be motion primitives-based kinodynamic RRT for autonomous vehicle navigation for complex environments, presented by Sambhu. Sambhu, go ahead.
Hello everyone, I'm Shambhu.
Is it
I'm a
audible?
master student at
Yes.
Okay.
Urbana Champaign. I'll be presenting my joint work with my colleague Mr. Shubham Kedia on motion primitive based kinodynamic planning for autonomous vehicle navigation in complex environments. The objective of the work is to design an executable motion plan for the vehicle to reach a desired goal configuration. Our motivation comes from the following challenges. Pure kinematic planners are not executable because they do not respect the non-holonomic constraints. In real world, it is quite challenging to model the dynamics of the system accurately, and search is hard in high-dimensional configuration space. Our key contributions are as follows. We demonstrate planning on a real autonomous vehicle using SLAM-based perception, RRT-based planning, and PID-based trajectory tracking and control. The trajectories are built using motion primitives that encode feasible motions. So our methodology is designed to operate under unknown dynamics of the vehicle. We demonstrate complex maneuvers like parallel parking, perpendicular parking, and reversing. Moving to the methodology, we consider 6 motion primitives as shown in the figure. The right and the left primitives are under full steering orientation. The extreme right figure shows the reachability tree under these primitives. The mapping and localization are done using Hector slab. Next, we apply rapidly exploring random trees to build a collision-free trajectory. Goal biasing ensures that the tree growth is directed towards the final goal. We use only neighbors as allowed by the motion primitives to build a trajectory and check for no obstacles along the path. We consider 4 basic actions: gear control, brake control, steering angle control, and velocity control. Later, we apply PID for trajectory tracking using the above controls. We give a video demonstration of 3 complex maneuvers: reversing, parallel parking, and perpendicular parking. Our experiments are carried out on a Polaris GEM E2 autonomous vehicle at UIUC. The vehicle is mounted with VLP LiDAR to perform Hector slab. The entire middleware for control is operated by ROS Noetic. The real-time control path traversed by the vehicle can be seen on the monitor. In the first video, the objective was to perform path planning with live obstacles generated from the LiDAR map. The second video demonstrates parallel parking by following a path that avoids any collision with the virtual cars parked to the front and behind the goal. The third video demonstrates perpendicular parking by following a path that avoids any collision with the virtual cars parked to the left and right of the goal. To conclude, we designed a motion primitive based RRT for collision-free trajectory planning on an autonomous vehicle. In contrast to the other RRT based works, our approach is designed to operate under unknown dynamics of this vehicle. The plans are feasible, but may be suboptimal because the RRT is a random planner and advanced planners like RRT star or its variants can be used for improvement. Thank you.
All right. Thank you, Shambhu. So are there any questions for this spotlight talk? Okay, so maybe Shambhu, really quickly, if you can briefly comment in a few words on the robustness of the navigation objective to more complex scenarios.
Yeah, so we have tested for only 3 scenarios here: the parallel parking, perpendicular parking, and reversing. So so the robustness means the approach is robust in some sense because the mapping is done using occupancy grain. So all the obstacles, right, are not like detected as point obstacle or some shape. It can be done for any kind of environmental obstacles. And but yeah, it doesn't consider the dynamic obstacles as of now. And the plan for the planning side, we found that it's able to actually found like a very small final configuration in configuration space, which are difficult to plan if we use the purely optimization based planners. So in some sense, we have not tested it properly to compare the robustness, but definitely it's able to find very feasible plans for different navigation objectives.
All right, thank you so much. Yeah. So our next speaker is going to be in person. I think Eduardo is in person. Okay, hey Eduardo. So Eduardo is going to be presenting real-time autonomous parking in unstructured scenarios with an indirect optimal control approach. And so would you be connecting to Zoom? Do you have a laptop? Like, okay. So maybe like a similar thing, you can just connect to Zoom and share your video. Yeah, just connect to Zoom and share the video. You have the Zoom link, right?
Yes, yes.
Okay. Seven, 8494. Yep. B18. This is your name. This is your name. This is your name. This is fine. Join. Okay. Yep. BAD. All caps. All caps. BADU. 22. Yep. Okay. Share screen is big.
Okay. Should I share my audio? Because I think there is some.
Oh, yeah, please, no,
I just
yeah,
play the
without
video.
the audio, and you can speak. Yeah.
Okay. Okay. But if I activate my microphone, it's gonna interfere with this one. Okay. Okay. Can you hear me? Okay. Hi, I'm Edoardo Pagot. I'm a PhD student from the University of Trento, Italy. I will talk to you about our autonomous parking scenario. Autonomous parking is still an open challenge. It involves path planning in unstructured scenarios. And here we focus on real-time requirements. So we choose a kinematic vehicle model. And you can see the equation there. And the reference frame of the vehicle model is on the center of the rear axle of the car. And we also have front and rear overhangs. And we choose 12 collision control points on the perimeter of the vehicle. And let's suppose there is one obstacle in the scenario. And the coordinates of each control point is passed as argument to the obstacle penalties. So when the collision control points is inside the obstacle, it's gonna have a value greater than 0. Otherwise, it will be 0. And we solve a minimum time optimal control problem. And we converted the dynamical system in its free time formulation. So in the Meyer term, in the target function, we minimize the final maneuver time. And in the Lagrange term, we minimize the penalty, the obstacle penalties. And we employ an indirect approach thanks to a custom solver, which is called PINS. And since we use the indirect approach, we can enforce the initial and final position as a boundary condition. So it's arithmetically respected. And we use an hybrid A-star algorithm just to create a coarse guess. Then we use a modified version of the original optimal control problem to track the course path found with the hybrid A-star algorithm. And then this new guess, it passes the real guess to the original optimal control problem. And we tested the problem in 3 scenarios: reverse parking, parallel parking, and a generic unstructured parking scenario. And from different starting position for a total of 63 maneuvers where the problem converges. As you can see, the car is getting very close to the obstacle and also performs complex maneuvers with more segments. And the average computational time is 0.6 seconds. So the system is suitable for real time and can be scaled for lower performance CPUs, like on cars. And the future perspective is to close the loop, to track the found plan, and create a full framework in a driving simulator. Okay, thank you, that's all.
Okay, thank you. Thanks, the speaker. Okay, so does anyone have any questions? Okay. So Edward, do you require lane lines in your approach? Because a lot of unstructured scenarios, especially like places like India, they don't have lane lines. So do you use those?
Actually, it's not mandatory to have lines for the parking spots, because basically the obstacles are just rectangles, so we can just model any scenario, let's say. So it's not a problem to have lanes. Obviously, the perception is totally
Perception required.
different problem for this framework.
All right, thank you.
Thank you very much.
So now our next spotlight talk is going to be by Vincenzo, and he's going to present data efficient, collaborative, decentralized thermal initial odometry. Okay, if not, okay. If not, I can play the video without sound and you can speak live. Does that work?
Yeah, that if you can do that is better because it's not so good there. Yeah. Wait, now.
Okay, so could you stop sharing?
That's a good. I can try. Okay.
Could you, stop?
Yeah.
Let me share my screen.
Okay, yeah, that's better. Sorry, I came here without a computer. Different agents and fuse. We present the first data-efficient, collaborative, decentralized thermal inertial odometry system. This work extends the JPL XVIO, a state-of-the-art single-agent thermal inertial odometry framework. We made XVIO capable of exchanging information between different agents and fusing them together to improve their state estimate. Last year, NASA successfully deployed the first helicopter on another planet. We want to show that having multiple drones collaborating helps in mission accomplishment and environment understanding. A drone swarm can explore vast areas faster than a single agent, so that tasks like exploration can be achieved in a shorter time, also impacting on the energy efficiency side. Not relying on a central unit that could potentially fail, invalidating the entire system, makes our approach robust. Also, decentralized systems are easy to scale and light in terms of memory and processing power. Recent advances in thermal camera development have made these sensors more affordable with higher quality and modest power consumption. Thermal cameras allow autonomous agents to operate in all types of light conditions without the need for an external lighting source. More than 3.5 times fast corners than the visual data in low light scenes. The development of collaborative setup allows the previous framework to receive and send data to the other agents and fuse the incoming information. We are going to talk about each of these new blocks, starting from the front end and tracks matching. We use an online photometric calibration algorithm to attenuate the disturbances and artifacts that thermal images are affected by. With this approach, we are capable to get 4 times more tracks than in the raw thermal imagery, and the feature matching is almost doubled. Key points detected and tracked in the front end are coupled with orb descriptors, and a binary vector of local aggregated descriptor is generated for each incoming image. The generated descriptor is sent to the other robots using the raw streaming system. We built an efficient request-response communication system that sends only the VLAN as request message to all the other robots. The results of our approach against the state-of-the-art of centralized collaborative system, COVINS, show that our work can use a quarter of the message exchanged within the system and requires less CPU and less memory concerning the other. The backend of our work uses the fusion data pipeline for MSEAF and SLAM proposed by Zhao et al. Using photometric calibrated thermal data and the collaborative fusion strategy can almost halve the absolute trajectory error of the system, bringing a significant improvement in the state of the art. Try it out.
All right. Let's thank the speaker. So any questions for Vincenzo? Okay, so I think in the interest of time, we're going to go straight to the last spotlight talk, which is a multi-event camera depth estimation and outlier rejection by refocused events fusion. Let me try and play this. I think the last video worked, so let's see if this works.
Stereo event cameras. We present event-based stereo depth estimation for SLAM in autonomous driving. In this work, we estimate the depth of dynamic scenes using moving stereo event cameras. The depth map on the right is color-coded with red nearby to blue far away. Due to high dynamic range, the event cameras can better perceive the scene in challenging lighting conditions where the frame-based cameras suffer, for example, when it's driving through tunnels. An event camera is a novel bio-inspired sensor that only responds to intensity changes in an asynchronous manner, thereby generating a stream of sparse events at microsecond resolution. Therefore, it removes data redundancy from static parts of the scene. Due to low latency, it produces almost no motion blur. It consumes very low power and has a high dynamic range. Using known camera poses, stereo events are back projected as rays into individual event ray densities called DSIs. These individual DSIs are then fused using element-wise operations such as the harmonic mean. Several fusion functions are proposed in the paper. Each voxel in the fused DSI counts the number of back-projected rays intersecting at that location. Sweeping across the depth axis, the edge features come into focus at the correct depth plane. The depth and its confidence at each pixel are extracted using local maxima of the fused DSI. We finally obtain a point cloud of the scene from the filtered depth map. We show results on the DSEC driving dataset comprising event cameras with VGA resolution. We compare our results with the state-of-the-art monocular method EMVS and stereo method ESVO. We can accurately recover more 3D edges than ESVO. Here, we can also recover the building far away, although the LiDAR-based ground truth is missing. Here, our method is the best at perceiving the traffic sign at its correct depth, and also removes outliers. We also report results on the head-mounted TUM-VIE dataset, the only 1 megapixel stereo event dataset. This scene is acquired using cameras mounted on a biker's helmet. Without ground truth from a motion capture system, we pre-compute camera poses using a visual inertial odometry algorithm. Even with noisy poses, we can recover cars, buildings, and trees remarkably well, while ESVO struggles with the high camera resolution. Compared to the monocular setting, stereo improves accuracy and speeds up 3D reconstruction, especially in case of small lateral motion like driving. We show that establishing event correspondences across cameras is not needed for computing depth. Our method estimates depth efficiently in challenging conditions. Even where LiDAR fails, it achieves state-of-the-art results and works well for multiple resolutions. Our code is publicly available. Thanks for watching.
All right, let's thank the speaker. So in the interest of time, we'll defer the questions to email. So if you have any questions, please contact Suman. Now we'll move on to our next set of invited talks. So I'm very happy and pleased to welcome Professor Max Schwager, who is a professor at Stanford University, and he directs the multi-robot systems lab where he studies distributed algorithms for control, perception, and learning in groups of robots and autonomous systems. He's won a number of awards like the NSF Career Award, the NSF Career Award, the DARPA YFA Award, and a number of Best Paper Awards, too numerous to enumerate. So Mac, welcome. Happy to have you here. And yes, please take the floor.
Great, thanks. Let me share my slides. Great, thanks. That was Rohan speaking, right?
Yes.
Great, thanks for the introduction, Rohan. All right, hi everybody. It's a pleasure to be able to join you remotely. I do wish I could have come in person. Kyoto is beautiful, and it's so fun to come to IROS and meet all the colleagues and all the friends. But reality is what it is, and so I'm here back at Stanford. I'm actually home in my kids' playroom, and that's why you see a bunch of funny blocks behind me, and the lighting is a little weird. So, well. I just ask for your patience, and it's also really late here. It's about 10:40, so I might be a little tired. Okay, so I'm going to talk about game theory and its application to predicting trajectories of other agents on the road and planning trajectories for an autonomous vehicle in autonomous driving. So here's the big picture idea. The traditional autonomy pipeline, you have some prediction module, which takes in raw perception data and predicts the trajectories of the other agents around you, the pedestrians, the other cars, whatever. And then given those predicted trajectories, we have a planner for the ego vehicle, which says, okay, I need to maneuver around those predicted trajectories to make sure I'm safe, to avoid collisions. And my thesis, my hypothesis in this whole talk is that this is kind of a flawed perspective, that actually prediction and planning are coupled problems, and that the future trajectories of other agents depends on my own executed motion and vice versa. And if we neglect this coupling, then we can end up with both unsafe systems and lower performance systems or inefficient systems. And so the core challenge here is, how do we simultaneously predict trajectories for other agents and plan our own trajectory in a way that respects this coupling? And the idea that I'm going to be proposing in this talk is that we should use game theory as a formalism to model this coupling and define trajectories that are suitable for all of the agents involved, both the ego agent, the autonomous car, and all the other agents. So the punchline is, we want to find Nash equilibria in the space of joint trajectories among the agents and the ego vehicle. And this represents simultaneous prediction and planning. So in this talk, I'm going to be talking about really two high-level scenarios. One is autonomous driving, where in the figure you see here, the orange vehicle is the autonomous vehicle, and the blue vehicle is the other agent. And so the orange vehicle is reasoning about uncertainty and predicting the trajectory of the blue vehicle, and then moving safely given those predictions, or I should say in a coupled fashion, predicting and also moving safely. And then the insight here is that this represents what we call a general sum game. I'm also going to be talking about racing, drone racing and car racing, where in fact this is also a game theoretic scenario. It's very similar to general autonomous driving scenarios, but this is what's called a zero-sum game. Now, the main difference between a general sum game and a zero-sum game is, as the name implies, the objective functions of all the agents involved in a zero-sum game have to sum to zero, and the objective functions in a general sum game don't necessarily sum to zero. In more plain terms, that means that in a general sum game, it's not necessarily true that the other agent's loss is my win, whereas in a zero-sum game, that is true. The other agent's loss is my win. So I'll be talking through specific algorithms that we've developed for both of these scenarios, both the general sum and the zero-sum game, and then applying those to autonomous driving and drone racing and car racing. So let's talk a little bit about the formalism of game theory. And in particular, I'm talking about what's called a generalized Nash-style game. So the best way to think about this is as a collection of coupled optimization problems, where each optimization problem represents the trajectory planning objective of one agent. So one of these agents is the ego agent, is the autonomous car, and the rest of the agents are have indices, I goes from 1 to n. And so we write down the objective function of agent I as ji, and the decision variables, which represent the control actions of that agent that result in the trajectory, those are theta I. And then the control actions of all the other robots, all the other agents in the scene, which are not under the control of agent I, those are called theta minus I, minus meaning just not I. And so what makes this a game is that the objective function is not only a function of my decision variables, but it's also a function of the other player's decision variables. And what makes this what's called a generalized game is that there are also constraints involved. So in game theory, generalized just means constraints. And so this is essential in robotics applications, in particular autonomous driving, because the constraints correspond to collision avoidance, and those are essential. In fact, in autonomous driving, right, if you don't have collision avoidance constraints, if the cars are somehow ghosts that could pass through one another, then it's not a game. Then every car can do whatever it wants, and there's no game theoretic interaction. So it's precisely the collision avoidance constraints that makes this problem interesting for robotics. And these constraints depend on the decision variables both of agent I and all of the other agents, because these are collision avoidance constraints. So this is not only me trying to avoid a collision with you, but also you have to try to avoid a collision with me. And then the definition of a generalized Nash equilibrium is it's a kind of equilibrium concept that, so there's no optimality concept because there's a whole bunch of coupled optimization problems. Instead, there's an equilibrium concept. And the idea here is basically that every agent's decision variables have to minimize their constrained optimization problem under the assumption that all the other agents' decision variables are fixed. But this has to be reciprocally true for all the agents. So another way to say this in plain language is no robot can unilaterally improve its objective. If everybody else is frozen, I'm doing the best I can do. That's the definition of a generalized Nash equilibrium. Okay, so we're going to talk first about zero-sum games because they're simpler, and the algorithm that we've developed for planning, robotic planning in zero-sum game scenarios. And then we'll talk about general sum games. So for these kinds of game theoretic problems, if you don't have constraints, there's a classic algorithm. It's called iterative best response that generally works pretty well across a large range of specific problems. It's very simple, and that's what's appealing about it. So let me describe how iterative best response works in the case where you don't have constraints, and I'll tell you why it fails when you do have constraints, and then I'll tell you about our algorithm, which is called sensitivity enhanced iterative best response, which can handle constraints. So the idea is very simple. Suppose that we are the gray drone and we're racing the green drone. So we first predict the trajectory for the green drone. What is the green drone going to do? And then we optimize our own best response to that prediction. And then we go and optimize green's best response to our best response. And then we optimize our best response to green's best response, and you iterate. That's why it's called iterative best response. And the Nash equilibrium is actually a fixed point of this best response map. So another way to say this is, if this iteration converges, it's not guaranteed to converge, but we find in practice in these planning problems it often converges if you don't have constraints. That's the asterisk. Then if it converges to a Nash equilibrium. So that's great. You found the solution that you're looking for. In practice, this doesn't work for constraints. So let's see why. The reason it doesn't work with constraints is because, again, step one, the green drone plans its trajectory. Now, what can the gray drone do? Well, it can just move out of the way. The only thing, so this is not a good option for the gray drone. The only thing it can do is plan a trajectory to avoid hitting the green drone. And then the green drone in the next iteration is perfectly happy. Why would it change? Because it already found its optimal path without worrying about constraints. So if you have a constraint problem, iterative best response essentially puts a huge advantage on the first player in the iterations. And it just doesn't lead to sensible solutions. So what we developed is called sensitivity enhanced iterative best response. The idea is, how can we allow for a constraint violation, or how can we plan to, let's say, how can we plan to push the other agent around a little bit by exercising our active constraints? And the concept is like this. Suppose that J is the other guy. J is the other agent, and I is the ego vehicle. So suppose J has just planned its optimal trajectory, and that's J sub J star tilde, or rather J sub J star. Now, what agent I does, the ego agent, is it expands a first order Taylor series expansion of this optimal cost. And what you find when you do this is that for the active constraints, if there's ever an active collision constraint in the solution, it's going to be exposed as this term you see here, where this partial g with respect to theta is the gradient of the constraint function, and then mu is the Lagrange multiplier that activates that constraint. And then you see that theta I now appears as an argument of the cost of agent J. So now theta I has a lever to go and change the optimal cost of agent J through this term, which we call the sensitivity term. Okay, great. So now this means that agent I can directly plan to make agent J's trajectory worse, to make their cost higher or to make their reward lower, whichever you prefer. And so what we do is we take this sensitivity term and we just append it to the objective function of agent I, which was J sub I. with a negative sign. So now we have a slightly different objective function for agent I, which basically says, yes, optimize your own cost subject to your constraints, but also try to penalize the other guy's cost. Make your cost lower, make the other guy's cost higher. Or if you're talking about rewards, make your reward higher and make the other guy's reward lower, right? That's the idea. So a couple of headline results about this algorithm. It's a fairly simple algorithm. It solves very quickly for these drone racing style problems. I'll tell you more about the specifics of how we formalize this as a drone racing problem, but it solves in about 20 milliseconds. And this is without GPUs. This is just a standard CPU implementation, nothing particularly fancy. Then we can also prove a theorem that the fixed point of this modify problem, even though we've modified the objective function of each of these iterates, the fixed point is still a Nash equilibrium of the original problem. It's just a Nash equilibrium that is much more balanced than the one that you would have found if you had used regular iterative best response. Okay, so we then formalize this iterative, the sensitivity of enhanced iterative best response for drone racing. It looks like this. So here's the drone racing track. Here's one drone. We have the center line in red. And the objective function is make it as far along the track, along the center line as you can within the time horizon. It's a receding horizon kind of an optimization. Subject to your own dynamics, you have to fly like a drone flies. Collision avoidance constraints, you can't hit the other drones on the track. Stay on the track, so you can't fly, you can't take a shortcut and fly off the track. And you have input constraints. You can't command arbitrarily high inputs. And this is a game only because of the collision avoidance constraint. This is the only place where these these multiple optimization problems are coupled among the different agents. And this goes back to what I said before, that in robotics, the collision avoidance is really essential in making this a game theoretic problem. Okay, so then we, as I said before, we implement sensitivity enhanced iterative best response to solve this game. And the result is what I'll show in the video here. So I want to be clear that this work is joint work with my former postdoc, Ricardo Spica, longtime collaborator, Eduardo Montijano, Eric Christofoulou, a former PhD student, and Zhao Wang, a former PhD student. So let me play the video, and you can see here, the green drone is using our sensitivity enhanced iterative best response. So this is a game theoretic planner. The blue drone is using the classic pipeline, which is just predict and then plan. So the blue drone assumes that the green drone is an immutable obstacle that it has to maneuver around. And you can see the advantage that the green drone can take. Using game theory, it can reason about what the blue drone is going to do and can essentially take actions to maneuver around the blue drone, and it immediately gains the lead and wins the race. We also have some onboard perception on this. I'm not going to talk about that in detail, but the robots are measuring one another's relative positions entirely from onboard cameras. Okay, so we've also implemented this same idea for cars and car racing. This is work by my former PhD student, Mingyu Wang. It's the same story. So the game theoretic car is in the back to begin with, and the standard MPC drone is in the front. And eventually that game theoretic car is going to be smarter in how it maneuvers, and it's going to enable it to take over the advantage and win the race. I'm putting short references here throughout, so you're welcome to refer to those references for more details. We've also implemented this on a full-scale autonomous car. This is called the X1 vehicle. It's a research autonomous car that was developed entirely by Stanford grad students. We teamed up with a lab that's led by Professor Chris Gerdes at Stanford to do this research. And in this case, we have the full-scale car driving on a racetrack and a simulated opponent, because we don't want two full-scale cars getting in a dangerous situation in this racing scenario, right? So we have the opponent is simulated for safety reasons. And in fact, the roles are a little bit reversed here. So here the game theoretic planner is in the lead and the MPC car is in behind, and the game theoretic car is able to defend its position and prevent the MPC car from passing. So overall, this game theoretic planner just makes a more intelligent racing vehicle. We have extended this to larger number of agents. Here's 4 drones flying in our lab with a little drone race course. And here's a simulation with 6 drones flying in a 3D race course. And we've done some various improvements to parallelize computations and to make things run on multiple cores simultaneously to make things faster. Okay, so this is fairly mature work. You might wonder, okay, great, it looks like things are kind of doing better with game theoretic planning sometimes, but do you have any hard data that backs this up? And the answer is yes. So I'll show you a plot with a 6-drone race. 3 of the drones are using a standard MPC, and 3 of the drones are using our game theoretic planner. And we've kind of shuffled the starting positions. Here's the starting box. As you can see, the green drones are game theoretic planner, the gray drones are MPC. And you see that no matter how you shuffle the drones, the game theoretic planner tends to come in first, second, and third place, and the MPC tends to lose fourth, fifth, and sixth place. And here, that's especially true in this particular shuffle. Okay, so the game theoretic planner really does produce a much more competent racing strategy than a typical MPC planner. The problem is this only works in a zero-sum game, because the whole philosophy here is that I can do better by making you do worse. And that's not true in general autonomous driving. It's true in racing. In racing, if the other guy's slower, that's just as good as if I'm faster. That's my whole goal, is to beat the other guy. But it's not true in general autonomous driving. So how do we deal with problems like freeway on-ramp merging, where I don't really care if the blue cars are optimizing their objective or not. I just want to get on the freeway safely, and I'm the orange car, right? A standard MPC method doesn't do very well here, and this is well documented among currently fielded autonomous cars. For example, Waymo cars around my neighborhood here in the Silicon Valley, you can see them freezing on freeway on-ramps. And this is what happens when you use the standard MPC pipeline, where you first predict and then you plan. Because the autonomous car can't reason about the fact that the blue cars are going to make way for the autonomous car. They just assume the blue cars are immutable obstacles. And so if you have a lot of traffic, that car is going to get frozen on the on-ramp. So how do we treat this non-zero sum game with a game theoretic planning framework? Well, we developed a new planner. It's called All Games. This is work together with my PhD student, Simon Lecleach, and a colleague, Zach Manchester, who's at CMU. So the idea is you take this Nash equilibrium, generalized Nash equilibrium game that I started with at the talk, so you understand what this is about, and you convert this constrained optimization problem to a kind of unconstrained optimization problem through the augmented Lagrangian. So what is the augmented Lagrangian? Well, it's the same as the Lagrangian. The Lagrangian, what you do is you take the objective function, and then you take a Lagrange multiplier times the constraint term and put that in the objective function. That's the Lagrangian. The augmented Lagrangian is the same thing, but you add another term, which is actually a quadratic term on constraint penalty. When you minimize the augmented Lagrangian, you actually minimize with respect to the primal variables theta and maximize with respect to the dual variables, which we call lambda. And the augmented Lagrangian is guaranteed to satisfy the constraints, just like the regular Lagrangian. It just has better numerics. It's better numerically conditioned. So what we do is we formulate the KKT conditions, what would be called the KKT conditions if this were an optimization problem, but we formulate the same kind of conditions, but for the game. Is the first order optimality conditions for all the coupled KKT systems for each of the agents. You get a huge collection of coupled KKT systems, and they're just represented by the gradient of this Lagrangian with respect to the primal variables are equal to 0. And I didn't write it, but also the gradient with respect to the dual variables are equal to 0. This is true for all the agents. So you get this huge coupled set of equations, and then you solve them with root finding methods. For example, Newton's method. You just solve for the solution of the KKT system directly. So this is our algorithm. The details you can find in this RSS paper, or an autonomous robots journal paper, which came out recently. It solves very quickly. For example, 38 milliseconds for 2 players. I'll show some more timing stats. An interesting finding that came out of this designing this algorithm in terms of a root finding problem for the KKT system is that, in fact, for these problems where the coupling comes into play as a collision avoidance constraint through the constraint, they always have not only a single Nash equilibrium, but a continua of Nash equilibrium. And this is kind of had been suspected by myself and other researchers in this game theoretic planning space, but this is a hard proof of the fact. And we basically looked at the Hessian of the underlying KKT system, and you find that it's always rank deficient, which means that there are solutions that can live in the null space of this Hessian. And physically what that looks like is essentially there's a whole continuum of Nash equilibria that are more or less advantageous to different players. I have a chat. What does it say? 2 minutes. Okay, great. more or less advantageous to different players. And so, in fact, what all games does is it finds what's called a normalized Nash equilibrium, which means it finds a Nash equilibrium which is equally advantageous to all players. It means that the Lagrange multipliers, the dual variables, are equal among all of the players, which means everybody is paying the same cost to enforce the constraints. So there's a certain notion of fairness. And here's another visualization of that continuum of Nash equilibria. Okay, so here's all games, the solution found for on-ramp merging. It can predict that this middle blue car is going to move out of the way a little bit, and the two end cars are going to widen a little bit, and that's going to give way for the orange car to move in. That's the Nash equilibrium solution from all games, which is very different from the MPC solution we saw before. And much more natural, right? Much more like what human drivers do. So we compared this with another general game theoretic solver. It's called ILQ Games. It came out about the same time. The lead author is a guy named David Friedrich Kale, who's at UT Austin. He was formerly my postdoc, now he's at UT Austin. And essentially we find that all games is faster in many scenarios, although ILQ Games is a wonderful algorithm as well. And a little distinction here is that all games enforces the hard constraints, the collision constraints, whereas ILQ Games actually represents those as soft constraints, as kind of soft penalty terms, and then solves that softened game. It also, this all games solves much faster than iterative best response, the algorithm that I talked about initially, but for general sum games. Okay, great. So the final thing I want to talk about is the concept of inverse game theoretic planning. Big question. We are supposing that the ego vehicle, the autonomous car, is solving this game for all the cars on the road in order to do a prediction for those cars. But how does it know what the objective functions are for those other cars? It doesn't, right? It has to make a guess. And if instead it could use observation data online to predict the objective functions of the other cars, it would be in a much better position because it doesn't have to assume that it knows those objective functions. So this is the problem that we call inverse game theoretic planning. It's analogous to inverse reinforcement learning or inverse optimal control. The question is, look at the trajectories, assume that they are solving a Nash equilibrium in this game, and then infer what the cost function must have been based on those trajectories. This is work, we call it lucid games. It's written about in this RAL paper from 2021. And I'm going to zoom through here. The basic idea is you have the objective function for the other agent, which is unknown. And we're going to suppose it's linearly parameterized. So we just have these parameters theta, which are not known. Features known, theta is not known. And what we do is we use a kind of unscented Kalman filter-like technique. So we suppose that these parameters are Gaussian distributed initially. So it could be a very wide Gaussian to start with. And then you sample sigma points from this Gaussian. And these serve as hypotheses for the objective function of the other agent. And then you solve all games with each of these hypotheses. So you solve all games for each of the different sigma points, and this gives you trajectory hypotheses for the other agent. And then you observe what the other agent does. Then you observe what the other agent does for 1 or 2 time steps, and you find out which of these sigma points agrees or disagrees with the actual observed trajectory, and you upweight or downweight the sigma points appropriately, and then you recompute the Gaussian, and then that's the UKF style algorithm. So eventually this will converge to the correct set of parameters. So you see these scatter plots of the different predicted trajectories here in red. Those are the different trajectories predicted with the different sigma points, and eventually they collapse to the correct prediction. So originally they're quite wrong and spread out, and then as the data evolves, they collapse to the right prediction. Okay, so we can also use this to impose safety constraints. So if we're quite unsure about the other guy's objective function, then we could have a high sort of keep out region for our planner. And then if we're quite sure, then we have a smaller keep out region. And then these would be reflected as constraints in the underlying game theoretic planner for the orange vehicle, who's the ego vehicle. And then that orange vehicle can maneuver safely given this uncertainty over the unknown objective function for the blue vehicle. Okay, that's all I've got. I hope I didn't go too far over. Thanks again to all my collaborators, co-authors, talented grad students, and so on. Thanks to all my funding agencies, and thanks to everybody at this workshop for your kind attention. And I'm happy to take any questions. Thanks.
All right, let's thank the speaker. Thanks, Mac. Always fun listening to you speak, and really, I do acknowledge it's very late for you, so we'll try to, take that into account. So any questions for
Any
Matt? Please
questions?
come up.
I'm not hearing
Yeah.
anything. Rohan, are you talking?
Yes,
Oh,
I am.
I'm sorry. I'm muted.
No, you're
sorry
not
about that.
muted.
Okay,
I
so,
can hear you.
okay, great. Any questions?
Yeah, go ahead.
Yeah, thanks for the great talk. I think it's really interesting, and I think this is exactly the right way to think about this coupled problem. One
Awesome,
question I
thanks.
had was that when the idea here is that you're kind of solving all of these coupled things at the same time.
Yeah.
And at least in the formulations that you showed, I think, unless I misunderstood, that everybody's kind of thinking about the problem the same way, as in they're all trying to do this sort of coupled solving. Can you talk a little bit about when that assumption breaks down and when, to take a bad human analogy, somebody just doesn't really care what everybody else is doing and they're just going to do whatever they want, sort of?
Yeah.
Not that's quite right, but can you expand on that a little bit?
Yeah, that's a great point. That's a really great point. So just to be clear, I don't think I made this clear, but all the computation here is being done by the ego robot. And they are computing the Nash equilibrium solution for the other agents as a prediction. So it's not that the other agents are computing a solution. We don't assume any communication. We don't assume anything about what the other agents are doing. We just suppose that the Nash equilibrium is a good prediction for the other agents. And it might not be. That's absolutely true. And part of it, meaning it might not be a good prediction, because there could be a bad driver, an aggressive driver, an extremely passive driver, and that's not going to really work with our framework here. Part of our attempt to address that problem was this last segment with the inverse game, where we can, using observed data online, back out the objective function of the other players that we're interacting with. But that doesn't quite go far enough, I think. Basically, there's an element of risk sensitivity or risk tolerance here. And my former grad student, Mingyu Wang, has done quite a bit of work on this to think about how can you infer the risk tolerance of the other agents on the road. In fact, we have a joint paper with Rohan in ICRA earlier this year where we did exactly that, where we used some of Rohan's graph theoretic tools to predict the risk sensitivity or the risk tolerance of other agents. So in other words, you can watch the behavior over a brief time window of the other agents and say, oh, that guy's dangerous, or that girl's dangerous. They're very risky, and I better just get out of the way. Or, oh, look, that person is super passive. This isn't going to work unless I take the lead and just take some initiative. So you can sort of infer that online. But I don't think that's the end of the story. I think that's a deep question and a very important question, and there's still a lot of work to be done in that area.
Great, thank you.
Sure.
Thanks, Mike. Yes, we have one more question. I hope you're not too exhausted.
So, hi, Mike. Thank you for the nice presentation.
Thanks.
A question about comparison to other existing methods. So you had the first comparison to MPC. I just wanted to know if you have had any kind of comparison to other common planners, such as, for example, tree search or any other planners.
Yeah, that's a good question. So that's a great question. I think we were really focused on continuous trajectory planning, meaning continuous state, discrete time, but continuous state. And so one could imagine like an MCTS method, Monte Carlo tree search method that searches a tree of decision options, and maybe that's what you're referring to. I have not seen this very commonly used in autonomous driving, although I think it's probably a pretty good idea. I think the tree search methods like MCTS work best in discrete state spaces. So you would, that's not to say there aren't versions that work in or try to work in continuous state spaces. There are, but I think they've had the most success in discrete state spaces. So for example, you could discretize the whole state space or action space and use MCTS and compare that. We have not made that comparison. I think that would take quite a bit of engineering, and maybe that would actually go into the territory of novel research. Also, these MCTS methods, at least they can be made game theoretic, but that would also require some careful thinking. I just haven't seen these tree search methods applied to autonomous driving in a game theoretic framework. But I suppose you could try to apply them without a game theoretic framework and still use a simple assumption for the trajectory prediction for the other agent. Yeah, it's an interesting idea. I have not done it.
Just a hint about using this concept as as for automated driving, as I referred to the other presentation today is from Tesla. As they mentioned that they are using that, and
is that right?
Yeah.
Oh, good.
Yeah,
thanks.
You can see some other works as in this area, maybe in combination with ML. That would be. I have a follow-up question, if it is possible.
Yeah.
I have seen that as you tested your concept as a lowest speed, as a 5 meters per second, as a, if I'm correct. Did you have the chance to test your concept for autonomous driving in dense urban areas?
Yeah, so there's a computational issue as the number of agents grows. I think the dense urban area is not an issue, and the speed is not an issue. In fact, yeah, I'd have to refer to the paper to see what speeds we're talking about in these scenarios that I'm showing, like the freeway on-ramp merging, but I'm pretty sure those are freeway speeds. So the speed is not a problem. The number of agents computationally, or rather, in theory isn't a problem. The problem is the computational time with a lot of agents. So if you had a scene with 100 agents, 100 pedestrians that you had to reason about in a game theoretic way, this would just take forever. There's no way this would be online. So you'd have to find a way to select the most salient, say 4 or 5 agents for the game planning to make this reasonable. Or you'd have to find a way to really, really accelerate this by parallel computation on a GPU. But I think all those are pretty interesting questions. Yeah.
Nice. Thank you.
Yeah, I think going just also to go back to the other work, I unfortunately didn't see the Tesla work that uses tree search. However, as a researcher in this space, I have to say it's quite difficult to compare one's methods with Waymo or Tesla or Uber, because those methods are not in the public domain. They're not published, right? These are proprietary methods, and you might see a talk, but that's not the same as an academic paper. So it's hard to know exactly what these commercial or I should say industrial outfits are using. So yeah, you can compare against published literature, but it's difficult to compare against hearsay from Tesla, for example.
Yeah, sure. Actually, I'm from Mercedes. I cannot talk about our concepts, but in the research, you will find there's several concepts in this area. Thank you for.
Thank you so much. Yeah, thank you. Thanks so much. You can hear me right now, back, can you?
Yeah.
All right, thank you so much. And I'm guessing you're not up for the panel discussion, which is in an hour and a half, right?
Yeah, I'll be fast asleep.
Yes. All right. Thank you so much, Mac. Thank you.
Thanks, everybody.
Right.
Thanks,
Good
Rowan.
night. Yeah.
Bye.
Okay, so our next speaker is Hang Zhao, who is an assistant professor at Tsinghua University. And prior to Tsinghua, he got his PhD degree from MIT and then worked as a research scientist at Waymo. His research on autonomous driving spans from perception, mapping, simulation, to motion prediction and planning. So let's all take a moment to welcome Hang. Hang, welcome, and take it away.
Thanks for the introduction, Rohan. Can you guys hear me?
Yes.
Okay, cool. Yeah, let's get started. Yeah, my name is Hang Zhao from Tsinghua University, and the title of my talk today is Interactive Motion Prediction and Simulation by Explicit Relation Modeling. But before that, let's have a quick intro of my lab called Mars Lab. We study and research data-driven methods for autonomous driving spanning perception, prediction, planning, mapping, and simulation. Autonomous driving technology has demonstrated the success in simple and homogeneous traffic scenarios, such as highways and sparsely populated urban cities. However, the real challenges today are in dense urban areas. As we can see, all the big companies are marching into big cities like San Francisco, New York City, Beijing. Downtown has an order of more road participants than suburbs. leading to more complex interactions between the vehicles, between the pedestrians and the cyclists. So in today's talk, I would like to show you how we model these complex interactions using data-driven methods and use it to empower multi-agent prediction and simulation. The first paper I would like to talk about is about interactive prediction. The title is called M2I, from factored marginal trajectory prediction to interactive prediction. This is a paper published this year at CVPR. Motion prediction is quite popular in the past couple of years. And today we already have a bunch of high-performing marginal motion predictors, such as multipath, TNT, waveformer. However, if we apply them on each agent within a very dense agent interaction scenarios, we're likely to see the prediction results to be unrealistic. And sometimes these results could overlap and collide in the future. So the question is, how can we obtain consistent joint predictions for multiple agents? There are a couple of naive solutions. The first one is that we can enumerate all the possibilities for each agent and then find the compatible solution among these combinations. For example, let's say we have n agents, each with k future trajectories. And then we have k to the n combinations in total. Then our task is to find reasonable results from these k to the n combinations. This exponential prediction space makes the problem really intractable. Another solution, the solution number 2, is that we forget about these explicit combinations and just use latent distribution modeling with deep learning methods. A typical implementation of this solution is that we use a graph neural network or a transformer to encode the features of each agent as one node in the graph. And then we send it into a generative model such as VAE or GAN to model their latent distribution, their joint latent distribution. At inference time, we need to sample from this latent distribution to get some reasonable results. The problem with this solution is that it's about its stochasticity. We have no control over what we can get, leading to poor interpretability. And it is not guaranteed to generate reasonable results either. Our solution called M2I is to factorize the problem. For each pair of agents, let's say in the data set, we classify one of them as influencer and the other one as reactor. Let's say we want to approximate the joint distribution of two agents, influencer and reactor, that is PYI-YR conditioned on X. X is the context of the scene. Then we can factorize it as a product of a marginal distribution of the influencer, PYI conditioned on X, and a conditional distribution of the reactor, that is PYR conditioned on X and YI. With this factorization, we greatly simplify this problem. Then the question is, how do we define influencer and reactor? We propose a simplified but very effective explicit relation categorization, yield, pass, and none. The definition of yield, pass, and none relation interaction is this. We check whether the future trajectories of these two agents cross spatially. If yes, and one agent will be the influencer and another agent will be the reactor. If no, if there's no conflict in the future, then there's no relation. And these two pictures shows two examples of no conflict, that their future trajectories are parallel. And another example shows that the blue car is passing the red car. So in this case, the blue car is the influencer and the red car is the reactor. With this definition, we can auto-label all the pairwise agent relationships in the dataset. So in our implementation, we auto-label the Waymo open motion dataset. Whenever we find a relation, we will use a red arrow pointing from the influencer to the reactor, as we shown in this figure. With all the labels prepared, we can start to train our M2I model. The M2I model are decomposing to 3 steps, and we have one neural network for each of them, for each step, but they share neural network backbones. Their only difference is that they have different heads. The first step, given a pair of agents, we will classify or predict their yield path non-relationships. Secondly, we will predict the mark. Let's say in this example, the blue car is influencer and red car is the reactor. The second step is that we predict the marginal trajectory of the influencer, as shown in the green arrow. Here we can use any existing motion prediction models, for example, like TNT waveformers. The third step, we predict the trajectory of the reactor of this red car conditioned on the predicted influencer trajectory. And in this way, we can get a scene-consistent joint prediction result. Here are some visualizations of this M2I model. In these videos, the blue car is the car we are interested in. As we can see from this example, the blue car is yielding to the pedestrian and another vehicle in front of it. And here's another example of the blue car yielding to a cyclist that's crossing the road. And the third example, showing the blue car is yielding to a jaywalker on the road. Okay, that's interactive prediction. And the next half of my talk is about interactive simulation. I'm going to talk about the paper InterSim, Interactive Traffic Simulation by Explicit Relation Modeling, that's published in this conference, IROS. The goal of interactive simulation is slightly different from interactive prediction. Interactive simulation has a very ambitious promise to test autonomous driving planners with complex scenarios within it, offline, meaning that we don't test it on the road, but within this simulator solely. A practical pipeline looks like this. The self-driving car fleets drive around the city to collect a lot of data and store them into the logs. And then we send the logs into a simulator to test the planner. An ideal simulator should be reactive to different ego plans, and at the same time produce diverse and realistic behaviors. Naturally, we want to use a learning problem to solve this simulation issue, as we hope it to learn from real-world agent behaviors. However, it suffers from a lot of challenges. I'll just list some of them. First, it suffers from sim-to-real gap. First, the sensor failures and noises are usually not modeled in these behavior simulators. Second, rolling out an imperfect simulator accumulates errors over time. Second, it also suffers from out-of-distribution issue. If we have unseen behaviors or states with sending into the simulator, it could crash the simulator. Thirdly, while temporal driving sequence has cause and effects, most deep learning methods have no sense of causality, commonly leading to deadlocks in multi-agent simulation. this phenomenon has been shown in many other simulators like SimNet. Our work called InterSim tries to solve these issues, but only partly. Let's see what we can do. First, InterSim is a realistic planner. It only perturbs the relative agents in the logs, meaning that it will stay very close to the playbacks in the logs. Second, InterSim avoids causal confusion with explicit relation modeling. This is very similar to M2I that I've just talked about. Third, it can synthesize diverse scenarios by manipulating the yield path non-relationships. Let's walk through the one-stepping process to illustrate the simulation pipeline. In this example, we have a line of vehicles are making U-turns in a very busy intersection. The cyan blue agent is the ego agent that we can control. And for the other agents, if they are in yellow, meaning that they are relevant agents. Other green agents are irrelevant agents. Let's start the stepping process. First, the simulator receives a new trajectory from the planner. And then we'll detect potential future collisions by checking the trajectories and bounding boxes of this ego vehicle and environment agents. In this example, we found that the environment agent number 1 will potentially collide with the ego vehicle. And therefore, we need to resolve this collision using a trajectory prediction method. For example, we can use TNT, waveformer. After resolving the conflict between the ego vehicle and environment agent number 1, we'll check the collision of environment agent number 1 with other agents. Here we found another collision of the environment number 1 with environment number 2. The environment agent number 2 is following the environment agent number 1. Because of the environment agent number 1 is going to slow down to yield to the ego agent, it could potentially collide with the environment agent number 2. So we further resolve this collision and adjust their trajectories. Similarly, we'll go on and resolve all the conflicts in the environment. After we resolve all the conflicts, we'll commit the trajectories and make the next step. Okay, and before we can use this simulator, a question is that how do we evaluate our simulator before using it to test planners? We propose 2 tasks. The first task number 1, is to see how the simulator reacts to proper plans. Here, the proper plan means that a plan that is very similar to the logs and that is also very reasonable. Here, the video on the left shows a dataset playback. And on the right, we slightly perturb the plan of the ego vehicle that is shown in the cyan color. And the simulator will react to the plan of this ego vehicle and will control this yellow environment agents accordingly. Let's see what it will do. Okay, then we have task number 2 to evaluate the simulator. That is to see how it reacts to novel plans. A novel plan means that a possible but very rare behavior in the logs. In this example, in the playback on the left, The gray agent is the self-driving vehicle, is the ego vehicle. And in the logs, the environment agents waits for the ego vehicle. And until the ego vehicle passes the intersection, it starts to cross the intersection. Then on the right, we start to manipulate the behavior of this ego vehicle. We let the ego vehicle to move to the intersection and wait for the environment agent. And our simulator sees that our ego agent is waiting for it. So it decides not to wait for the ego vehicle and to cross the intersection by itself. Also, thanks to the explicit relation representation within intersim, we can also perturb the predicted relations and test the planners with diverse scenarios. For example, what we show here is that the vehicle on the main road originally is predicted to wait for another vehicle that is turning right. However, we can manipulate it, perturb their relationships so that the agent on the main road will pass the vehicle that's turning right, showing that our ability to generate diverse and new scenarios. Okay, and let's have a quick summary of what we have just talked about. First, yield pass none is a powerful explicit interaction representation, and it can help joint motion prediction. And this explicit relation also helps to generate robust and realistic interactive simulations. Finally, our intersim simulator beta has already been released. It supports closed-loop simulations on datasets like Waymo Motion Open dataset and the New Plan dataset. It can manage your simulations with our dashboard. You can also use it to visualize and debug simulation results with Python in your or just in your browser. We have a quick demo shown on the right. We have a dashboard that you can select what kind of simulations you want to do and select a log. You can also import your own planners. And finally, the simulator will simulate the scenarios for you. Of course, intersim is still at a very early stage. We welcome everybody's input. For example, if you want to improve our simulator, you're welcome. You're also welcome to use our simulator to evaluate your planner. Okay, finally, I would like to thank my collaborators. Actually, these two papers are mostly done by the first author, Chao Sun. And I would also like to thank other collaborators from MIT. Thank you. Any questions?
Okay, so let's thank the speakers. Thank you so much, Han, for the great talk. So now we can open the floor for questions. Okay, so maybe Ang, I can start out with one question. So traffic in different regions, traffic in different kinds of countries, different kinds of cultures, they have different ways of interacting with each other. Could you comment on the transferability of your relation learning component as to what are the assumptions and limits of learning a relation model in the US versus in Japan versus India? So how does the relation interaction module transfer in these different kinds of regions?
Thanks, Rohan. I think that's a very interesting question. That's true. behaviors are very different. I think, yeah, the behaviors of the agents across different countries are very different, and that's why using a learning-based methods will be, or a data-driven methods will be a very powerful tool to solve these issues. And I think that in order to deal with different interactions in different countries, even in the same country and different areas, I think the behaviors are quite different. And I guess we need to train new models for each of them. For example, a model that is trained in New York City might not transfer to to Arizona. Yeah, I think that's not possible. And I think when the self-driving car operation moving to a new country or even a new city, we need to retrain the model. But luckily, yeah, these are all data-driven methods, and hopefully data can solve these issues.
All right, thank you so much. Let's thank the speaker once again. And so now we're going to be making a slight change to the plan. Originally, we had a break scheduled for after Hang's talk. However, since we fell a little bit behind, so now we're going to instead have Shimon's talk right now, and then we'll have the break right after Shimon's talk, and then we'll follow that up with the panel. So Shimon, are you ready to present now?
Yeah, let me just share my screen.
All right. Okay, so let me first introduce Shimon. Shimon is a professor of computer science at the University of Oxford and a staff research scientist at Waymo. His research focuses on deep reinforcement learning and learning from demonstration. Welcome, Shimon. Could you try that again?
Can you see my slides okay?
Yes.
Okay, and you can hear me fine, I guess?
Yes.
All right, shall I get started then?
Yep.
Okay, well, hello everyone. Thanks very much to the organizers for the invitation to speak today. It's really a pleasure to be here and to have the chance to tell you a bit about some of the work we're doing at Waymo Research on learning realistic and diverse agents for autonomous driving simulation. So Waymo's mission is to build the world's most experienced driver, both for moving people through Waymo One, which is our fully autonomous ride-hailing service, and for moving goods through Waymo Via, which is our trucking and local delivery service. Waymo cars have driven more than 20 million miles on public roads and more than 20 billion miles in simulation across 25 cities in the United States. That's equivalent to hundreds of years of human driving experience, and that experience benefits every single Waymo driver in our fleet. Now, what I want to focus on today is how we can use this experience offline to train and test new releases of autonomous driving software in a simulator. Now, 20 million miles of real data may seem like a lot, but it's not nearly enough to validate the Waymo driver in a scalable and repeatable way. We need simulation to give engineers feedback during development, to test how our driver handles rare and safety critical situations, to discover novel issues we haven't observed in real world driving, and to validate software updates. And it's not just about testing either. The holy grail of autonomous driving simulation is to have a simulator that's reliable enough to use for training the autonomous driving software itself. That means that the machine learning models underlying that software are trained directly on data generated in simulation without a human in the loop. Achieving this is really challenging, and it requires an extremely high level of fidelity and robustness in the simulator. And one of the biggest challenges in building a simulator with the requisite fidelity and robustness is modeling the behavior of other road users. the human drivers, cyclists, and pedestrians who share the road with our cars. And this is where learning from demonstration comes in, as it gives us a powerful tool for extracting those behavior models from the 20 million miles of real world data that we have. Now, a naive approach to modeling other agents is just to replay their log behavior. The example shown here makes clear why this is not an adequate solution. The real world driver was in the state represented by the green box when it observed the objects in the pink boxes. Now, the simulated behavior of a new version of the software is shown in blue. Prior to this point, it performs slightly different actions, causing it to diverge from the green box and arrive at the intersection later. Because the agent coming from the right is just replaying the log, it doesn't react to the changed behavior of our driver, and its left turn, which was innocuous in the real world, becomes a simulated but unrealistic collision. Now, to do better, we need these agents to react and do so realistically when our driver takes a different course of action than in the log. This requires closed loop control policies, which we can learn from demonstration. So the main idea is to treat our 20 million miles of real data as a set of demonstration trajectories, and then use learning from demonstration algorithms to synthesize models of human road user behavior, which we call sim agent policies. Now, in our approach, even in simulation, everything starts with data. What I mean by that is not just that the agents in the simulator are trained from data using learning from demonstration, though of course they are. I also mean that the unfolding of the simulation itself is data-driven. So every simulation rollout is paired with a real-world run segment, like the one shown on the left. And a run segment is essentially a joint trajectory consisting of log states that were recorded by a Waymo car out on the road, as well as other details like road layout information. The rollout begins by placing the Waymo driver in the same initial state as the Waymo car was in at the start of that run segment, and spawning an agent at the initial state of each of the other road users in the scene. As the simulation unfolds, the Waymo driver diverges from the log behavior because it's controlled by different software than was used when the data was collected. Now, formally, we can model the problem of how sim agents should react to the simulated Waymo driver as a Markov game with an unknown reward function. We have available a data set of joint demonstration trajectories produced by the experts, that is, the human road users whose behavior we want to imitate. The states in these trajectories are inferred from LiDAR and camera sensors on the ego vehicle, that is, the Waymo car used to collect the data and processed by Waymo's perception systems. The resulting state estimates have three kinds of features. First, they have static scene features like location of lanes and sidewalks and information about the road graph, which is a set of interconnected lane regions with ancestor, descendant, and neighbor relationships that describe how agents can move, change lanes, and turn. Second, we have dynamic scene features like the state of the traffic lights at an intersection. And third, we have agent features, which are like the position, velocity, orientation of the other road users in the scene. As I said, the simulation is data-driven, so it's based on a logged reference trajectory and populated with some combination of playback agents, which just replay the logs, and interactive agents executing closed-loop control policies that are learned from demonstration. Okay, now to tackle this problem setting, we developed Symphony, which is a new approach to learning from demonstration for autonomous driving simulation. At the core of Symphony is a standard learning from demonstration algorithm like behavioral cloning or MGALE. And on top of these, Symphony contributes two novel additions. First, a parallel beam search refines policies on the fly by pruning branches that are unfavorably evaluated by a discriminator to ensure the simulation produces highly realistic behavior. Second, a hierarchical approach factors agent behavior into goal generation and goal conditioning to produce agents with diverse intents and ensures we reproduce the full distribution of realistic behavior. So let's take a closer look at the parallel beam search. In the typical adversarial method, the discriminator is used only during training. By contrast, in Symphony, it's also used to shape behavior during inference. As we've seen again and again with methods like AlphaZero, when we have access to a model of the environment dynamics, combining a policy represented as a neural network with online refinement with the tree search is a really powerful approach. However, there's an important difference in our case. In AlphaZero, as in traditional model predictive control methods, an agent simulates various futures before selecting a single action to execute in a target environment. By contrast, in our setting, the simulator is itself the target domain in which we deploy our agents. However, because simulations happen in parallel, promising branches can be duplicated during execution to replace unpromising ones, focusing computation on the most realistic rollouts. So here we can see the parallel beam search in action by visualizing all the parallel rollouts simultaneously. Brighter shades indicate rollouts that are rated as more realistic, whereas darker blue shades indicate unrealistic ones. And as expected, turning before or after the passing car is rated as realistic, while crashing into it is rated as unrealistic. So we compared Symphony to baseline methods that don't employ parallel beam search on a data set of over 1 million run segments. The results show that beam search greatly reduces unrealistic behavior like collisions and off-road driving. However, using beam search hurts the simulator's distributional realism because it prunes away diversity, encouraging mode collapse. We quantify this with a new diversity metric that we call curvature Jensen-Shannon divergence. It measures the difference between the simulated and log distributions of turning behaviors. More specifically, it's the Jensen-Shannon divergence between the empirical distributions of average curvature between simulation and reference logs. If you consider a four-way intersection where you can like turn left, turn right, or go straight, we can quantify how often drivers go left, straight, or right by computing for each branch point in the road graph the average curvature as drivers pass through this intersection. If we repeat this process for a number of branch points, then we get an empirical distribution of average curvature. And we can create these distributions for our simulation, and then another one for the reference logs, and then compute the JSD between the two. If we look at the empirical distributions themselves, and not just the JSD, we can see the loss of diversity manifested as underrepresentation of right turns, as you can see in the figure. Fortunately, the diversity that the beam search prunes away can be recovered using our hierarchical goal policy. Here, control of the agent is split between a goal generating policy and a goal conditional policy. So the goal generating policy is used to sample a goal conditioned on the first state of the rollout. The goal then remains fixed throughout the rollout to model consistent intent. The goal generating policy is trained to match the empirical distribution of goals in the demonstration data. The goal conditional policy takes this goal in the current state as input and specifies the probability of the available actions. In addition, the discriminator also conditions on the goal, evaluating realism in the context of the given intent. Goals are represented as sequences of road graph segments, as these constitute routes, and these routes capture high-level intent and are a primary source of multimodality in the data. So the figure on the left summarizes the whole Symphony setup. The goal generating policy, which is shown in orange, samples a goal conditioned on the first state of the rollout, which then remains fixed. The goal conditional policy, shown in green, takes this goal and the current state as input. Then during execution, rollouts are performed in parallel by sampling actions from the goal conditional policy and refining them on the fly using the parallel beam search. Now, if we combine the parallel beam search with the hierarchical approach in this way, we can get the best of both worlds, which is what the results on the right show. We retain the realism of beam search, but also greatly improve distributional realism as measured by curvature JSD, recovering the diversity that was pruned away by the tree search and more. So this video clip illustrates qualitatively how tree search can improve agent behavior. In red, we have a baseline behavioral cloning agents that crash into each other in the intersection. By contrast, in green, we have our Symphony agent using tree search in which one agent yields, thereby avoiding a collision. Here we have a similar example where the behavioral cloning agents in red collide, whereas with the Symphony agents, one yields in order to avoid colliding. And here's one more example in which one of the behavioral cloning agents in red takes the priority and then starts driving into oncoming traffic. By contrast, the Symphony agent in green yields, allowing that oncoming traffic to pass through the intersection first. So the results I showed you are actually only a sample of the experimental results we obtained, which can be found in our recent paper. In addition to the results I mentioned, which were obtained on a proprietary data set of over 1 million run segments, we also have results on the smaller but publicly available Waymo open motion data set. We also present results when Symphony uses behavioral cloning as its core learning from demonstration method, and when it uses MGALE instead. We find that the former performs slightly better, probably because it's less susceptible to mode collapse. Our main results are on short rollouts, which last 10 seconds, but in the paper, we also present results on longer rollouts of 20 seconds. And the results I mentioned have 2 interactive agents, and the rest are playback agents. But we also present results scaling this up to 8 interactive agents at a time. So let me finish by saying a bit about what I think some of the open questions are. So first of all, there's a lot more to be done on generating and measuring diversity. So far, we only measured diversity of intent, but there are other types of diversity, such as driver persona, that we'd ideally like to model. In addition, our hierarchical agents, they're based on road graph goals, which are great for cars, but they aren't suitable for other types of agents like cyclists and pedestrians that might not follow road graph segments. So we've also developed hierarchical agents that use latent goal representations to address both of these issues. We also need to expand our suite of metrics to measure diversity. While curvature JSD is great, it only targets diversity of intent. So if we're going to tackle those other types of diversity, we need metrics to assess that as well. Then there's the challenge of partial observability, which is currently not modeled by our agents. And this creates a number of subtle issues. So first of all, perception errors in the data can confound the training process. For example, imagine a car that's driving down a narrow road with parked cars on both sides. Even small errors in estimating the size of the car's bounding boxes will make it look like the car is crashing into all the parked cars that it passes. If we then treat this as a demonstration to learn from, we're basically teaching our agents that crashing into cars is good. So we need to develop noise-aware learning from demonstration methods that are robust to this sort of issue. In addition, some of the log behavior may not be explainable without a model of the driver's partial observability. For example, information gathering actions like creeping forward in an intersection to see around a building, these actions don't make sense unless we understand the driver's occlusions. So capturing this sort of behavior requires more sophisticated agents than what I've presented here. And finally, since the purpose of simulation is ultimately to model the real world from the perspective of the autonomously driven vehicle, we also have the challenge of viewpoint sim, of recreating in simulation the partial observability, including the perception noise that the vehicle would experience when out on the road. Another challenge is synthesizing behavior at the tails of the distribution. While we've shown that hierarchical agents can improve diversity, at best, this means we're capturing more of the modes. But rare events like collisions, they just don't happen often enough in the data for any learning algorithm to effectively pick up and recreate them in simulation. So this is a big shortcoming because assessing the behavior of the Waymo driver in rare and risky situations is a crucial requirement for simulation. So to tackle this problem, we're developing approaches that use adversarial agents together with our tree search methods to actively upsample events such as collisions and then filter them against a stringent standard of realism, which is provided either by human labelers or realism models that are trained from the labels they produce. And finally, we have the challenge of co-training sim agents with the planner module in the Waymo driver. There are huge potential advantages to such co-training in speeding up performance improvements through the use of things like adaptive importance sampling and adversarial training. But there are also risks of things like overfitting that require care and attention to prevent. So to conclude, Symphony is a powerful new approach to learning from demonstration that enables realistic and diverse simulations for autonomous driving software. If you're interested in this work, as I mentioned, we have a recent paper with all the details. It was published at this year's ICRA conference, where it was also nominated for Outstanding Learning Paper. Okay, thank you for listening. I would be happy to answer any questions.
All right, thanks, Shimon. Let's thank the speaker. All right, questions? Yep.
Hi, thanks for the great talk. You talked about it very briefly at the end, but I was hoping you could expand a little bit more on the simulating tail behavior part. One of the things that I often think about when thinking about trying to create really realistic simulators from data that we can actually collect in the self-driving world is that we kind of are necessarily limited by the things that we see, even though we want to use those simulators to, you know, train our ability to do things that are you know, not that we haven't seen, but maybe we haven't logged specifically. Can you talk a little bit about the intuition about that simulating tail events, and maybe expand a little bit more on what you said at the end of the talk there?
Yeah, sure. I mean, I think dealing with rare events is one of the, or perhaps the fundamental challenge in self-driving. So from a simulation perspective, I agree with everything you said. This is a really big challenge. The simulator is really not that useful if we can't model rare events well, because that's really the main thing you want to test. And you just don't have the data to do it. So there aren't any good answers here. I think, as is often the case with self-driving, the question is more, what is the least bad answer? So, you know, you have several options about which poison you want to pick. So one solution that I was alluding to at the end there is basically that you fill the gap in the data with some human labels. So there's like two aspects to the problem. One is like, can you generate the rare interesting events like collisions? And then the second question is, can you reassure yourself that they are realistic? So, you know, using things like upsampling with these parallel beam search, adversarial agents, adaptive importance sampling, we do have a toolbox that we can use to generate the interesting rare stuff that we care about. So that's not too bad. The question is, how do we know that any of that is realistic? Because we're pushing our simulator out of distribution. So how do we know that it corresponds to the real world? And there isn't an easy way to do that, but one way to do that would be to just show the stuff that you generate to humans and ask them whether it's reasonable. And then use that to filter the unreasonable stuff that you generated, or use it to train some kind of discriminator, which you then use to automatically filter stuff that you generated later. That's, I think, one sort of possible approach to make progress on this very hard problem.
Great, thank you so much.
Also from my side, thanks for the interesting talk. I have one question of whether you have thought of comparing your closed loop rollouts also to, for example, prediction approaches on the new scenes data set, which of course don't deal with the closed loop issue. But yeah, I feel like it would still be interesting to see how this compares. Does it make sense to you?
I think I understand what you're saying. So we've thought a lot about the other direction, which is like taking open loop trajectory prediction, behavior prediction tools, and seeing how they perform closed loop. So then you get this covariate shift problem that, you know, is well known from methods like behavioral cloning. And the question is, can you fix that problem? So can you do some model predictive control or something, do something in training to try to address covariate shifts, so you can take your powerful behavior prediction tools and use them for closed loop control. I personally have not thought that much about the other direction, like taking closed loop stuff and seeing how well it does at open loop behavior prediction. I guess on the assumption that because the closed loop prediction problem is harder, it won't be as good as something that focuses on trajectory prediction. But I have to admit, I don't have data that specifically supports that claim.
Yeah, thanks a lot. So I see your point, and it does make sense this way, but I think it's interesting to see how large the gap is, right? With this closed loop, which is of course more challenging, how close you can get to the open loop task. Thanks.
Yeah, that's fair.
Okay, any other questions? Let me just quickly check Zoom. No, chat. Okay, no questions on Zoom. So Shimon, maybe I can just wrap up with one final question. So you presented Symphony, and it's quite apparent that moving forward, simulators are going to be really important for autonomous driving, especially in unstructured scenarios. So I guess an open question is, how do you measure the quality of a good simulator? You mentioned realism, diversity, but moving forwards, do you think we need like a formal objective metric that like an entire research direction or research thrust can use to build good quality simulators? How do we measure objectively the quality of a simulator?
Yeah, that's a good question. That's a really big question. I think the answer here ultimately has to be some mix of quantitative and qualitative stuff. So, you know, part of the point of the Symphony project is that realism is not enough. We also need distributional realism. That's why we developed this curvature Jensen-Shannon divergence. And, you know, that's only one of like a suite of distributional metrics that we look at. And you know, I think that's like a useful step forward to look at distributional realism and not just realism. But there's still, I think, two big issues. So one is when you have a suite of distributional metrics, how do you like combine those into a single scalar performance? If you're better at one distributional metric and worse than another one, what does that mean? Does that mean the simulator is better or worse? So there's an aggregation problem there that makes it hard to go fully quantitative. And then the other issue is related to the previous questions. You know, what about realism at the tails? So these distributional metrics, they have the problem that they tend to be dominated by mode behavior. If you match the modes well, then the fact that you are totally missing some important tail behavior won't be manifested by distributional metrics. We can try to come up with quantitative measures of tail realism, but of course, you know, there are thousands of different tail behaviors, and only some of them are interesting from an autonomous driving perspective. So there needs to be some subjective element in there to say, okay, which forms of tail realism do we actually care about? So somehow we have to find the right combination of those components to try to get an overall measure that's actually useful for figuring out if our simulator is good.
Okay, thank you so much. Let's give another round for Shimon. Thank you so much, Shimon. And thank you for your time. This workshop has been crazy. It's morning for you. Half of other speakers are speaking at night. So this hybrid participation has you know, taken us all for a turn. But thank you so much. And okay, so now we will head off into our 15-minute break. So the break is going to be from 4:10 to 4:25 p.m. And we will meet back around 4:20 or 4:25 p.m. for the panel discussion, which is going to be very interesting. We have 5 panelists, 2 on Zoom and 3 in person. So please get back here at 4:25 for the panel discussion. Thank you. We're going to wrap the conference, this workshop up with a panel. And this panel is titled basically, can we achieve level 3, level 4, level 5 autonomous driving in the next 5 to 10 years? And what is it going to take to get to that stage? And let me just introduce our panelists for today. Our first panelist is Zhao Tang, who is a research scientist in the robotics team at Google Research. He is leading the navigation and locomotion teams. Zhao's research is to develop machine learning techniques that enable robots to navigate in human-centered environments safely, efficiently, and in socially appropriate manners. His research interests include reinforcement learning, foundation models for robotics, navigation, and legged locomotion. Welcome, Zhao. Our second panelist is Joydeep Biswas, who is an assistant professor of CS at UT Austin and an adjunct assistant professor at the College of Information and Computer Science at UMass. He received his PhD in robotics in 2014 from CMU and his BTech at the IIT Bombay. His ultimate goal is to have self-sufficient autonomous mobile robots working in human environments, performing tasks accurately, robustly. In support of this goal, he is interested in research in perception, planning, and control applied to autonomous mobile robots. Welcome, Joydeep. Our third panelist is Professor Hang Zhao, an assistant professor at IIIS, Tsinghua University. He is the principal investigator of the Mars laboratory. His research interests are multimodal machine learning, autonomous driving, and computer vision. He was a research scientist at Waymo, and before that, he got his PhD at MIT under Professor Antonio Torralba, and an MS degree under Professor Ramesh Raskar. Our next panelist is Rowan McAllister. He is a machine learning manager at the Toyota Research Institute in California, focusing on autonomous vehicle planning. Previously, he was a PhD student at the machine learning group with Carl Rasmussen and a postdoc in the robotic AI and learning lab with Sergey Levine, working on probabilistic modeling toward data efficient reinforcement learning and autonomous vehicle planning. And finally, our final panelist is Shimon Whiteson. Shimon is a professor of computer science at the University of Oxford and the head of research at Waymo UK. His research focuses on deep reinforcement learning and learning from demonstration with applications in robotics and video games. He completed his doctorate at the University of Texas at Austin in 2007 and spent 8 years as an assistant and then associate professor at the University of Amsterdam before joining Oxford. He was awarded a starting grant from the European Research Council in 2014, a Google Faculty Research Award in 2017, and a JP Morgan Faculty Award in 2019. So please join me in welcoming all the panelists at this panel, at this workshop. Okay, so the way I'm thinking we should do this is that I can start off by asking 1 or 2 questions, and we can take turns through the panelists to answer that question, and then we can open the floor for questions from the audience. So, okay, so let's maybe start with a very general but very difficult question. What are the limits of current machine learning and deep learning technology? Deep learning is ubiquitous in autonomous driving and self-driving and ADAS, but how far is it going to get us? We are right now where we are, we know that, but in the next 10 years, if we want to make the next breakthrough, the next revolution in autonomous driving to get us from where we are right now to a bigger jump in terms of scalability in the hands of consumers, to make autonomous driving and ADAS cheaper, is the level of deep learning enough currently, or do we need a breakthrough in terms of deep learning algorithms, or is it a question of compute? So that's the first question. What are the limits, and how do we break through those limits? And I'll just open it up to the panel. Whoever wants to go first can go first. All right, great.
I'll take a stab at it.
Oh. All right, Shimon, go ahead.
So I would say there's sort of 4 essential ingredients. So we need good learning algorithms. We need high fidelity simulators. We need tools for dealing with rare events, and we need to address reward design. So if we look at the current state of the art, I would say we have very good learning algorithms. We probably take that for granted, and that's not really that unreasonable. High fidelity simulation is hard, but a lot of progress is being made on that, as was discussed at this workshop. Rare events, as I said earlier in answering a question to my talk, I think we have statistical tools like adaptive importance sampling for generating upsampling rare stuff, but we don't have enough data to tell us whether that's realistic. So that's a fundamental obstacle. But the final one that I would really underscore is reward design. If we're going to move beyond imitating what we see on the road in order to have robust control systems, we will need to be able to pin down objectively and quantitatively what is the definition of good driving behavior. And at least in the published literature, I think very little progress has been made on that. And that's probably the biggest single obstacle we face today.
Okay. Yeah.
Sure, I can add to that. I think I second what Shimon said about like the tails of the distribution. But I would like to add, I think another thing which is rather important to have is competence awareness or competence estimation. We try to think of like our policies today of like, here's your state, here's your observation, what should your action be? Sometimes it should be normalized to say that the correct action is to say, I'm not sure. I don't know what the correct thing to be doing is. And I think there's a lot of improvement that can be done in that regard.
I also want to add a few things. One is I feel that learning algorithm is pretty powerful nowadays. I think people might not understand it. Recently transformers, large models is pretty powerful. Just look at the large language models or visual language models. And even we are dealing with a decision making problem, like sequential decision making problem. New techniques such as decision transformers also transform that decision-making problem to supervised learning problem. So I'm not too worried about the learning algorithm or the architecture. To me, I feel the difficult part is data collection and data processing. We need a lot of data to train large models. And I know that maybe for self-driving car, it seems that we get a lot of data. But the problem is a lot of these data are not that interesting, right? If the cars drive like without any interesting incidents, these data, although we have a lot, it's not very interesting. But then how do we identify or mine all these data to get the interesting events and then upsample them? These are I think, unsolved problem yet.
Look, I think there's a lot of interesting problems in the way, and I think it's still very much a science, not purely an engineering. I think a lot of people, including the public, the way sometimes people talk about autonomous vehicles is it can almost be, thought of as an engineering problem. But I think, there's still a lot of years left of research as kind of especially things like machine learning make its way through the stack from perception from maybe 2012 onwards to prediction, maybe from 2017 onwards to maybe more recently planning, which is really hard to do with safety critical systems. And I think one of the kind of insidious things is that you can get something working 99% of the time and you can do a demo and you can show investors and everyone can be very impressed, but it's really the long tail of events as some of the speakers here today have been talking about that really prevent getting to 100% autonomy and close to 100% safety. So I think the long tail of rare events, it's a huge scientific and important problem to solve. And at least my kind of general thoughts about this is that, can we come up with machine learning algorithms, if they're going to be more and more prevalent in autonomous driving, that better generalize and also better adapt to new situations? So I think humans are really good at thinking on higher levels of abstraction that generalize much better out of distribution. Waymo actually has sorry, I didn't see all of your talk today, Shimon, but I know Waymo has this example where sometimes, tail events, you see like there was one where a motorcycle is just riding itself down a highway. And it's because the rider came off previously, but the motorcycle, it had momentum. And, you ask any human what's going to happen and they can give you intelligent answers. They know there's a lack of intelligence there, so it'll probably not do any complicated turns or anything, but they know it has momentum. They've never seen this before, but they can still reason about this. And same thing when humans are driving on, say, snow for the first time. They can adapt within a few tens of seconds, even though they've never witnessed this before. So I think learning systems that better generalize and adapt will probably really help us in those long tail events in the future.
Actually, just remember, I think on the topic of tools, what tools can help improve the state of the art. I'm actually very interested in neurosymbolic approaches. And Rowan was just talking about like the momentum of this entity going down the highway. That's a symbolic concept. You shouldn't have to like go through a deep learning model to reason about like physics, right? But on the other hand, like perceiving that thing is actually quite hard, right? So I think there's a lot of advances left to be made on how do you jointly learn both the neural components as well as a symbolic component, so you can leverage the best of both worlds.
All right, thank you. Hank, do you want to add? Yeah.
Yeah, I agree with the other panelists about that. First, learning algorithm should be the core of understanding human behaviors. And also the simulator is the core. But at the same time, I also believe that algorithms beyond learning algorithms, they are also equally important. What I mean by other algorithms beyond learning algorithms are, I can give some examples. Like, for example, like say we find an interesting case in our logs, and can we find equally interesting or very similar events from these from the logs? These are like data mining algorithms. Although does not sound like that fancy, but in practice, we find it really hard to design a nice algorithm for that. I think that's the first thing, algorithms beyond learning algorithms. The second, I think how to develop efficient human-in-the-loop development process is also very important. I believe most of the engineering efforts today are like we have a triage team to find out interesting case and assign these issues to different teams to solve it. And I think in the future we need a more efficient process. We definitely need humans in the loop to tell us what are interesting cases, which are critical cases, to give us some sparse labels. But I think this process can be made even more efficient in the future, that the learning algorithms takes most of the job, and humans just give involve very little in the whole process, but still give guidance to the improvement of the whole system.
All right, thank you so much. Before we move on to the next question, does anyone in the audience have anything to add or like a follow-up question to ask on this topic? Okay, so you guys mentioned like Shimon and Zhao, you both mentioned like needing more data, and that is like one way to solve the long tail distribution. But now the question is, we already have a lot of data that's captured in the US, UK, and in developed countries. But now if we want to talk about autonomous driving in places where autonomous driving has not developed so much, and this includes developing countries like, for example, India. And there are a ton of open research questions and open questions on how we can start developing autonomous driving in these areas. And the first step, I guess, is to collect a bunch of data. So in order to motivate and encourage or to facilitate development and future efforts along the lines of promoting autonomous driving development in places like India, how would you suggest would be the best practice or best ways to go about starting the process, starting the data collection process, starting the thinking of ways of what kind of algorithms to develop? What would be a roadmap or a process of starting to move towards autonomous driving in developing countries? Again, it's an open question, so anyone can answer.
Can I be controversial and say rely less on data?
The more controversial, the better. Please go ahead.
If you rely less on data, then you don't have to worry about like collecting the data. That's one stance. The other stance is that maybe even if you do rely on data or rely on cheap data, maybe you don't have to like drive your superly instrumented vehicle over there. You can actually ask a person to collect like cell phone data, which is, and also especially if you don't need labels for that. So my thoughts are rely on less data, rely on cheap data.
I slightly disagree on rely less on data, because obviously people drive very differently from United States versus at India, right? So I think it's very hard to set up some rules if you don't have data to show you the difference. So my I'm thinking out loud. It's maybe you can start from development countries, collect a lot of data, but develop the algorithm that is easily like adaptable, as you mentioned. So there's a lot of like meta learning algorithms that can develop fast adaptation techniques. So then you can use a little bit of the real data or the target domain data, for example, from India, from China, from Japan, and then quickly adapt the policy towards these new countries.
Yeah, so just to add to that, so Rowan mentioned in his previous answer that we face scientific challenges and not just engineering challenges. When we get to the point that we're focusing more on engineering challenges, I think one of those challenges will be, how can self-driving companies make their operations, their processes efficient enough to quickly deploy in a new city in a way that actually makes business sense, without having to collect so many miles in a new city that it's too expensive to even worth contemplating doing. And I don't think any company really has that worked out yet, even if you're talking about transferring from one American city to another American city. When that problem is solved, I think it probably won't be hugely difficult from a technical perspective to generalize to other countries. I agree, the answer probably involves meta learning or transfer learning. But yeah, that's an engineering problem which remains on the horizon for now.
Yeah, so I think I sympathize a lot with the kind of less requirements on having large amounts of data. Yeah, mainly because I mean, this is the first time I've been in Japan for this conference, and like I could walk out of the airport and rent a car. I have zero data of driving in Japan, and yet they'll hand the keys over to me, and they're happy to insure me and everything. So like how is it that I can do that? How is it that any of us can do that? And I think we do have these powers of generalization and adaptation, but that's also like maybe an idealistic point of view. Like I think the more pragmatic point of view is, if we do have data, like why not use it? And so then like Joydeep was saying, yeah, I mean, if we have cheap data, that's obviously going to be better. I think companies that sell vehicles as opposed to selling rides or something else, they have the advantage that if they are selling vehicles, they can record data with the customer's permission for free, effectively, and so you can, you can kind of record that data preemptively. But I think it is nice to think of solutions that don't require this, thing of like, oh, I want to deploy in Malaysia now, but oh, we're gonna have to go collect some data first before we can even think about deploying. It makes sense in the short term, but I think longer term, maybe 10 years from now, it would be nice if we didn't have to think that way.
I personally think that relying data should be fine. I mean, relying on data, even on large scale data, should be fine, because in perception or in deep learning computer vision, like we have already proved that if we have larger models, we have more data, we can develop like unsupervised learning methods to do some pre-training so that the downstream models performs very well. So I think engineering wise, this type of solutions like pre-training, fine-tuning, and downstream deployment. I think this process is already very scalable. So I think relying on data should be fine. But I think the real challenge on the behavior side is that our algorithms are not really relying on data. It requires a lot of handcrafting algorithms in it, making it untransferable to new environments. So yeah, so I think still developing new algorithms that is less reliant on human inputs should also be a very important thing for us to look at.
Thank you. Thank you so much. I guess the reason why I ask these questions is because, as panelists, you all are a mix of academia and industry. And the question now is that there are future leaders who are applying for autonomous driving research as grad students. People are right from undergrad, high school level. They're all interested. They keep asking me like, how do I get into autonomous driving? So, what is the right problem space for research if you want to get started in autonomous driving research? And why I'm asking this question is because this question has two perspectives, one from the industry perspective and one from the academia perspective. What people are working on has the flavor of the problems you both are working on is slightly different. Because in academia, you might have a very state-of-the-art algorithm that's like cutting edge, has all the right numbers, beating all the benchmarks, but it doesn't work in practice because it's not scalable. It's not easy to use. The code is very messy. A grad student wrote it. So how, given the difference of the gap between industry, what's going on in industry and what's going on in academia, if you were to advise a new grad student as to what is the right thing to work on, is it infrastructure? Is it tool development? Is it algorithmic? Should you be working on data set collection? Like, do you need to work on an image net kind of like a problem statement? Do you need to work on a simulation environment like Symphony? So what is the right problem space for someone who's entering autonomous driving research?
I can attempt an answer to that from a reinforcement learning perspective, because that's my area of expertise. So like a few years ago, I would have said the time is not right to apply reinforcement learning to autonomous driving. So developing expertise in reinforcement learning might be great for a lot of careers, but not for autonomous driving. Now I think that has changed a lot. I think the time is ripe. I think a lot of people are looking at reinforcement learning techniques as a key tool in cracking the control problem for autonomous driving. But I think, I always tell students in my intro reinforcement learning course that, reinforcement learning takes as a given the reward function. It assumes that you have Oracle access at least to samples from a reward function. So I think actually, developing expertise in reinforcement learning algorithms themselves is not like is not addressing a bottleneck in the industry. I think expertise in like human in the loop machine learning, human computer interaction, issues about preference elicitation and reward design, that's where a huge amount of expertise will be needed for reinforcement learning to successfully be used in autonomous driving. And that's actually where there's a lot more added value than in the core reinforcement learning algorithms themselves, for which that expertise has become much more commonplace.
So I will try. I think this question, where a graduate student should start, I think there's no right and wrong. There's all the things that you mentioned, like a reinforcement learning or even safe reinforcement learning, quick adaptation, simulation, data collection, data set, all these are very good starting point. I really don't want to give people a suggestion, say this is the most promising one and sort of corner people to one direction. I think the beauty of robotics or self-driving is we actually don't know which one will work. So try to explore. I do want to acknowledge there's quite different flavor if you are doing research in industry versus in academia, because in industry, usually we have the data and we have the compute. So people is more likely to want to scale up things. For example, a lot of things I want to do is to have tons of data and design like a data mining algorithm to figure out what are the interesting data, or develop a simulation that can consume all these data to make simulation more realistic. But maybe in academia, it's very hard to do so. Then it's more about like a data efficient algorithm or a safe reinforcement learning algorithm or fast adaptation, which might not need a lot of data. But I would encourage students to actually experience both sides, right? Doing an internship in industry and also doing research in schools to experience both sides. I think that will be helpful.
I have one meta insight on someone getting started in research on try to figure out what the directions would be, which is get your hands dirty, like try out existing approaches. Don't just read papers. I think the moment you actually start trying out, actually deploying existing code or existing algorithms, you start realizing what are the corner cases, what are the edge cases, what's the limits, and so on. And the second thing that I would add to that is that don't devalue time spent on building tools. I feel like good tools make good, like drive good research. And I think even in my lab, I try to encourage students in developing good tools, which will catalyze forward future research.
Yeah, lots of really good points here that fully agree with. Yeah, especially the reward design Shimon was mentioning, and also doing internships and or exchanges to other labs. I think, like me personally, I got most of my ideas when I was doing my PhD, and then I interned at Uber ATG, and then it was fascinating to understand what they were working on, but then also trying to gel that with my PhD work, because there's all of these interesting differences, and it just sparked up all of these ideas. And if you exchange to other labs, often each lab will have different philosophies, and there can be really interesting ideas when you look at the kind of intersection in the Venn diagram. So I think that's often a good way to kind of come up with interesting research ideas when you kind of get outside your own bubble, which can be very easy to put yourself in, in any institution without moving around too much. Beyond that, I think, like kind of hybrid systems, how can you, merge like imitation learning and reinforcement learning, and like, and also how do you like combine that with priors? Like, I mean, autonomous driving is this interesting robotic challenge where humans already know how to do it. And so, not only can they provide demonstration data, but they also write like, rule books for the road that like, specify all of these things. We don't need to kind of relearn everything. So yeah, like in a Bayesian sense of like, I've got all this prior information and now I've got this data, how do I combine them to come up with a really good like posterior model? And also thinking a little bit further down the line of like, maybe not jumping on bandwagons or anything like that, but like kind of like thinking, maybe what might be more useful 5 years from now. So like something that might be more useful 5 years from now is like personalization. If we are to sell autonomous vehicles and not everyone wants their vehicle driving the same, how might we do that? And also things like, maybe coordination of vehicles. It doesn't really make sense to work on at the moment because there's not that many autonomous vehicles on the road. But you can imagine a future where it's like 50% of the vehicles are autonomous. And then it makes sense for those vehicles to, communicate observations or, communicate more than just a blinker, but, much richer information. And, while it's not relevant now, it could be much more relevant a few years from now.
Yeah, I also think that actually the grad students are actually in very sweet positions. Like since self-driving has a great promise, but it is not fully solved now yet. And they can do internships in the companies to know about the problems, but they will not be constrained by all the rules in the companies or all the product pressure from the company. They can explore new paradigms for new solutions. For example, as the other panelists say, that we can explore like a combination of learning algorithms with symbolic algorithms. We can explore learning algorithms and other like optimization, search algorithms. We can explore causalities, safe RLs. Yeah, I think there are a lot of free space to explore for the grad students. At least for now, yeah, self-driving is still not that close, or for self-driving is still not that close. Yeah, I think they are in a good position.
All right, thank you so much. I think at this point, we want to open this up to the floor. If anyone wants to ask the panelists any question, please feel free to come up to the mic. Yep.
Yeah, thanks for providing some interesting discussion. I guess not to sound too much like a pessimist, but with the announcement this morning that Argo AI is shutting down, I guess what are your thoughts as far as what the future of the industry might look like if this is a winter that is approaching us? Thank you.
I don't think it's a winter. I think it's a consolidation, and the consolidation was expected. A lot of people saw it coming. It's not a big surprise. I think self-driving is a hard problem, and the only players that have a chance of succeeding at it are those that are in it for the long haul, and that's what we're seeing reflected in what's happening in industry.
I think there's, let's see, there's a lot packed into that question. So I think the question is like, are we actually making progress? Yes, we're making progress. Will we get there? Will we get to level 5? I think level 5 is really hard. And I think it requires a lot more than what we're doing, way more than what we're doing. Should we stop working? Or of course not. And I think in academia, we tend to have like a longer horizon. Like we're actually, Rowan raised like several really good points of things that we should be looking at in the future, personalization and so on, and like new learning techniques and so on. And I think these are the things to be working on. I don't know, that's my take.
I totally agree that L5 is a bit far away, but for companies, maybe finding the right strategy to monetize the current technology on more controlled environment might be quite successful strategy. But for research, I think we should continue doing it. It's not only for money, it's also for science.
Okay. So, yep, we can go to the next question. You were first, yeah.
So I wanted to ask, you mentioned that, carefully using our data or using all the data that is available to us, but being aware that our approach should not rely entirely on data, since it might, have bias, or it might not be possible to have large enough data to reduce that bias. Could you tell me how to go about this? Like if you approach a problem in this sense, and in autonomous driving, it seems so contextual. So what kind of approaches can you use to use your data efficiently, as well as ensure that, context is being communicated into your algorithm?
I could actually talk a little bit about some of the things that we're working on to that regard. So one of the lines of research in our lab is introspective perception, which is trying to ask the question, what in your sensed data is likely to lead to failures? And this is less about like, take your sense data and produce a result. It allows the algorithm to say that, based on what I'm saying here, I don't think I can give you a meaningful result. And there's like several reasons for that. There's maybe the input is inherently noisy, or maybe it is that you just haven't gotten enough data to actually understand how to convert it into a meaningful result. And this is the difference between aleatoric and epistemic uncertainty. But I think these are the ways in which we can start thinking about, do we have enough data? With the data what we have, like how confident are we? And these are the ways we're starting to think about this.
Okay, thank you.
Hang and Shimon, was the question visible, audible on Zoom? Okay, just making sure. Okay.
Okay, thank you.
All right. Does anyone else want to take a stab at the question? If not, we can move on to the next one.
Yeah, it's not a great answer to your question, but I think this is an important for the community to think about, you know, where you do have data and where you don't have data. Like, so, you know, the situation we don't want to end up in is if like cars drive really well around Mountain View, where a lot of wealthy people live and, you know, and work at some of these companies, but then, you know, maybe in areas outside, get underserved because, the autonomous vehicle performs more poorly and is therefore more dangerous. And so I don't know the best solution to this, as you know, but things like diversity and hiring and there's all sorts of things in which we could keep doing to be a bit more conscious of this problem. I don't know the answers, but it's a really important point for a variety of reasons. Yep. Thank you.
Right. Thanks. Who was next? Okay, go. Yeah.
Yeah, so maybe kind of combining the two previous questions. One of the things that I was thinking about when Rowan, you made your comments about, how do we like do this, like step back and like see things semantically and not need new data for, these other sorts of things like that. In this industry, in this research field, whatever, depending on whether you're the industry, the academic side of this, can you folks comment a little bit on, are there going to be pathways that are actually just dead ends, but are actually quite useful dead ends and certain time horizons that we won't then end up like, so for example, I'm just going to tell you my bias here. I don't think we can just data our way to L5. I don't think that's going to ever work. That's a personal bias of mine. But maybe we can data our way to something that's like a useful product that can then buoy the rest of the research necessary to do something totally different, on the way, or maybe not totally different, but at least significantly different on the way to some other place. And maybe that will only get us so far. And then we have to do something again that's different. I'm curious if you think that there's value in pursuing some of these things that may or may not really take us all the way, may or may not generalize in the manner the very first question that was asked. Anyways, there's just a thought that's in my head.
So I think I think the short answer to that is yes. It's kind of like, like why do science? And sometimes you don't necessarily know the exact goal that you're trying to go for, but sometimes you only get solutions in roundabout ways by kind of breaking apart from the crowd and not jumping on bandwagons, but like trying something else, and maybe you actually discover something surprising that you wouldn't have otherwise that could help with problems that you care about. I mean, in terms of not coming up with things that solve all of L5, I think it's I mean, there's plenty of ways that it can still be useful, and a lot of companies try to make the problem easier for themselves, which is kind of like a nice solution. So like Neuro, for example, doesn't have to transport humans and rapidly, so they can take side streets, they can go a bit slower. It doesn't matter if someone's groceries get to them 15 minutes, like not ASAP. Or trucking companies can get really used to certain routes and just and that can be beneficial to them, and solve like a subset of the problems that is still something that's quite useful. But I think more generally, I mean, one of the things I love about autonomous driving is it's just this gold mine of like machine learning research ideas. Like there's so many things that go into it, like mapping and coordination and planning and prediction aware planning and stuff like this that I think just for the sake of for academia, it's kind of like a big benefit where often half the challenge of is us being able to think up ideas, and I think autonomous vehicles, this space, it often presents a lot of really interesting ideas on a silver platter for us. And hopefully that has spin-off effects in other areas, not just for the autonomous vehicles.
I really liked your framing of the question of like, are there valuable dead ends? And that made me think, okay, so I think one way I can think of dead end being valuable is that it allows you to discover insights to the problem. So an example of that is like, I don't believe we can do this with like end-to-end deep learning, but let's say you do end-to-end deep learning with some limited data and it's performing well. And then you investigate like to perform well in this limited data, what was it doing? And then you realize maybe, for example, that it's doing like time prediction of like what you're seeing and forecasting. That gives you some insights of how you can better modularize and formulate this this problem, and then take the next step forward and reformulate this problem and move forward. So I think there's definitely value in like going dead ends, which as long as they reveal insights to the problem. Yeah.
I also want to use that end-to-end as an example. Originally, I believe a lot about end-to-end learning, and later I find that it's very difficult for self-driving cars due to the data requirement, due to safety, interpretability, and so on. But I want to say something like, now dead end is only conditioned on time. So maybe today it's a dead end, but a few years later, due to self-driving cars or all these cars with great sensors on the road, then we have tons of data. Maybe the interpretability of neural network get improved. It might not be the dead end. It might be a new research direction that's very promising.
I also want to add to that. I also found that people in both industry and academia are exploring like new ways, both scientifically and also commercially. For example, in China, I observed that some startup companies that are developing robo sweepers that are basically the robot cars that are driving on the slowest lane of the road and tries to sweep to the road. I think this is of course, it will not make the biggest amount of money, but I think it is a starting point for as a company to make some money and collect data on the real world scenarios and develop algorithms to make it better. And I think, yeah, there are some ways to actually, even with the existing technologies, we can still iterate on the products maybe slowly, but we are always getting improved. And probably in the future, we get some breakthrough technologies that can make use of the existing data and make good use of the existing robot hardwares. And yeah, probably we'll have a breakthrough in the future.
Thank you.
Yeah. Okay, Shimon, were you saying something?
I was just going to say, it's a cliche to compare self-driving to like a moon mission. But I think one way in which the analogy is apt is that we can expect the technology we develop to affect a lot of related industries. And all the problems we've been talking about, these are the same problems that arise in any other robotic system, autonomous system, safety critical system. So we can view the self-driving industry as a catalyst for investing large resources into these challenges that are going to arise again and again, you know, as we work towards improving artificial intelligence for many domains.
All right, thanks.
Thank you. Yeah, next question.
Thank you. Yes, I think we all agree that to become good at planning, we need good simulation, because we can't just test it all on the road. And then for like, I think we would need at some point good metrics to evaluate planning in simulation. But to get there, we first need to know, and that's what Shimon mainly talked about, I think, also to have good driver models and to be able to compare them to like how realistic are they. And looking at for example, the plot that you showed, or the table, there's like 100 metrics or so, and it's like in prediction, L2, off-road collision and such stuff. But you can be, I don't know, like better here, but still not human-like. So do you also, or I think you also see that as problem, but how can we solve that problem? Maybe that's the nicer question.
Is that a general question or targeted to someone specific?
No, I mean, general question.
Okay.
I think Shimon will say some words, but also the rest is, of course, very invited.
Yeah, so this is, I would call this the problem of selecting the meta metric. you've got all these metrics, but how do you aggregate them into a single meta metric? And at the risk of sounding like a broken record, this is the same as the reward design problem. When you're choosing a meta metric, you're just facing this problem at test time. How do I know whether my system is good? Whereas with reward design, you're trying to decide how you should train the system. But it's the same problem. And I think we need to do a lot more research on how to do reward design. Obviously, we'll need humans in the loop. So we need some kind of preference elicitation. We need to develop, I don't know, Turing tests or like mechanical Turk pipelines, figure out what is the right interface for which we can efficiently extract preference information from humans so that we can start to pin down what we mean by good driving. Because at a certain point, we won't be able to get by without that.
So maybe to briefly add, so I think that there's a distinction, right, between the reward for how you want to drive and then what you see what humans do, what you certainly don't want to do yourself, but you still need your simulation to like also contain those samples, right? Does that make sense? So I agree, it's a similar, yet with this difference that your simulation agents are like maybe unsafe and violate the traffic rules and so on. But for like reward design, you could say, okay, violation of traffic rules is in the first place a bad thing. There must be a reason for violating or so. Does that make sense? So this and yeah, I'd say like the simulation agents, you can treat them like in prediction, right? Whether behavior is human-like or not, but then the planning behavior should be on a higher level, right? We don't want to be average human, but we want to be much better and safer.
Yeah, I totally agree, but like one thing I didn't actually realize until I started working on autonomous vehicles is that distinction is smaller than you might expect, because paramount to the self-driving car is to be safe, and one of the most important ways of being safe is being predictable, and being predictable means acting like other road users. So imitating humans actually gets you a long way towards normative driving behavior. But in a way, this is actually a problem, because I think what's happening is that enables imitation learning to be kind of a crutch that we're all relying on. We can make a lot of progress with imitation learning because humans are pretty good drivers, and because acting like humans means driving predictably and therefore safe. But at a certain point, we will run out of road. And to bridge that final gap, even if that gap is smaller than you might have expected, to bridge that final gap, we will need to pin down a normative definition of good driving. And we need to start on it now because it's a very hard problem.
All right, thank you so much. Maybe we're going to have one final question. Yeah, go ahead.
Thank you for the amazing panel discussion. Actually, I had one question about like simulation is getting very ahead. Like we are observing very good results in simulation. So what is what is your opinion on getting that good result? Like, is there a direction to transfer that learning? Because RL is doing amazing in simulation. Like you can do wonders in simulation. Like recently we are trying to train adversarial agents to attack the ego vehicle. The ego vehicle avoids those agents, like predicts all the bad situation. But transferring that behavior is what is your opinion on that direction? And I have an additional question, but thank you for this.
I feel like I have to repeat a famous saying: simulations are doomed to succeed. Well, okay, but on the other hand, I think there's a ton of work recently, and I think Shimon talked a lot on how we can leverage real data to improve your simulations and all. I think that's a direction to be going, that you can get a lot of good results in simulation. And when your real world results don't agree with the simulator, then you can think about like, well, what is broken specifically about this difference in the simulator? Don't just try to improve your simulators for everything blindly. Think about like what is not working in the real world, which your simulator said should have worked. Maybe that's the way to think about it.
Thank you very much. And my last question, like final one, is like, what is your take on having many sensors versus like just cameras, or like because we humans just see things. We don't have like point cloud is so like LiDAR are so amazing, like they can see so far away. But we just rely on very limited vision, but we're still able to drive perfectly well. So what is your take on having many sensors versus just cameras?
Okay, I didn't know if you wanted to speak first, Shimon, but go for it if you want.
Okay, I can comment on that. Yeah, actually, my background is more about computer vision. So I personally think that the vision sensor is definitely the most powerful one. And improving the visual capability of the visual model, the visual perception model is the most important thing, I think, in self-driving perception. Because the LiDAR perception is already doing very well. However, still we are not able to solve many long tail cases. For example, with LiDARs, it's really hard to see the many fine grained details, such as the age of the person, the eye gaze of the persons. We really need a much stronger visual model to help us to better understand. It's not about detection, it's about scene understanding, to understand what's happening in the scene. Like if the elderly is looking at us, if he can walk very well on the street or not. Or there are many other cases. For example, we see postal cars, right? Postal cars and a postman, and they behave very differently. These two agents, a postman and a postcar, their relationships are very special. And this information can only be extracted from visual data. Yeah, so that's why I personally believe that we should improve on the vision side. But at the same time, I believe that LiDAR is necessary. It's definitely necessary. Or we can also develop like 4D radars. Probably maybe still need some time to develop to help us to better understand the 3D structure of the environment to ensure safety. So yeah, my personal view is that vision is the very basic building blocks for perception, and on top of it, we use other sensors to help with the safety.
Yeah, so I think it's a really good question, and different companies think about this different ways. But also because of the economics of it. But like I think ideally, like use as much information source as you can. So like, and I think the advantage of combining things like LiDAR and radar and infrared and vision and stuff like that is you have a lot of redundancy, but they're also strong in different areas. So, you know, LiDAR will obviously see fine at night, and, you know, radar has different properties when you're looking through rain and smoke and stuff like that, or fog. And so I think one of the advantages here is you can go so far beyond what a human can do. And it's one of the advantages, it's one of the hardware advantages where you can, you know, drive, you know, go beyond level 5. And I kind of wish there was like a level 6 for us to aim for, where it's like, you know, don't just drive as good as a human can do in all conditions, but like drive way better than them. So I think that's the grand hope that a lot of us kind of think about. Yeah, and so yeah, I'll leave it at that.
Just very quickly to answer your question, I think it's a trade-off along different axes, right? So one axis is to get the best result possible by leveraging all possible information. The other axis is, you know, it's science. Can we develop a artificial driver that use only a pair of eyes and as good as human? And the third axis is probably cost, right? So if we want to make money to build a company that sell cars, we cannot have too much cost on these sensors. So depending on what's your purpose, you are going to make different trade-off along these 3 axes. So personally, I'm a researcher. I feel self-driving is so hard a problem. We should leverage as much information as possible by combining all kinds of sensors.
All right, thank you so much. Anything anyone else has to add? All right, well, I think we can wrap this up.
Thank you very much.
Yeah, thank you. And remember, if you hear anything about level 6, you heard it first here at this workshop. So we want to patent that now. Now, okay, so thank you so much, Shimon, Hang, Jie, Joydeep, and Rowan. Thank you so much for your time. I know it's been a lot, Shimon, you've been hanging on for a long while. So as Hang, so thank you so much for sticking around and participating and volunteering your time as the most precious commodity of all. So thank you so much. And hopefully you'll be
for organizing.
Yeah, thank you.
Yeah, and hopefully you guys will be available for future editions. I definitely want to explore future editions of this workshop. So yeah, I'm looking forward to interacting with you all in the future. All right. Thank you so much, everyone. Thank you for coming.
It's nice meeting you. Yes, nice meeting you. We'll chat more. Yeah. Rohan just shared one of your recent papers on our lab Slack. We were reading about the prediction work.
Oh, the prediction conditional goal.
That's right. So
Yeah.
let's move on.